I may work on the user vision systems and in WHL, broader application. So I hope to not tell you stuff that you know. But I saw that you see mostly. So I don't repeat myself as a theory journey. So I would like to start with a metaphor. So imagine a mosaic artist arranging tiny pieces into a masterpiece, right? So each project alone is meaningless, but together they form a complete and detailed image. So in a similar way, vision transformers break an image into patches, analyzing their relationships simultaneously to grasp the bigger picture rather than isolating details. So, Transformer revolutionized AI in 2017, so it's a passion, right? And is a model to focus on different parts of an image. So by 2020, this was applied with the vision, with vision transformers, which process entire image at once, and this capture complex relationships more effectively than earlier models. So that's why they are transformed with AI and application across multiple images. Okay. So we have, for example, numerical images, so are announcing a diagnostic by representative tumors and anomalies in high precision. Or, for example, in self-driving cars, they improve real-time perception. Or in security systems, for example, in fashion elimination, for identity verification. And last, in the application that we all know, so generative AI side. But what makes these models so powerful and so different from early AI models? To understand this, I try to take a little step back and to look how computer vision have evolved over time. So at the beginning, we had this hard-coded vision model, right? So where in the 60s to 80s, more or less. So AI relied on MCAP rule, right? So using edge detection, or for example, geometric shapes and feature templates. Okay, so by late 80s, researchers shifted toward training models to learn patterns. And this need a shift from data instead out finally then finally. In the 19th and 20th and the first years of the new millennium, we saw a shift to machine learning to visualize. So I really all know what this meant. So the breakthrough came with, for example, convolutional neural networks or Kunda neural network, that's inspired by human visual system. So something that I think that is good to notice for what concern our talk about visual transforming is that despite CNN's success in pattern detection, they started with long range relationships image. And then we arrived to transformers. But so transformer origination and the AI, and the reason is that the EITs expect, for example, to CNN and our tools analyze data image at once. So much like how humans taking a world see. So this global processing makes them exceptionally effective at capturing complex relationships. So I try to explain it beyond pretty magical, right? So imagine you are in a meeting with 10 people discussing an important topic. With sequential listening, you listen to each person one by one, normal, right? So, but only after speaking with the 10th person, you understand everyone's speech. Okay, so the key limitation that we might forget or misinterpret what the first person said by the time you would last, right? With CNNs, like convolutional neural networks, you don't listen the conversation sequentially, but you focus on each data. Okay. And for example, you group together people based on proxy. I would say that the key limitation is that you get a detailed understanding of, for example, small loops, but you might lose, for example, long-range relationships between peak and simplified part. And then we have the last part, right? Our vision transformer. So I will go and speak at once. Okay? And somehow you understand everything and focus on what's important, right? Without losing track of the use conversation. And the key strengths that is of this method, of this model, is that it captures both local and global relationships in the conversation instantly. So this trend is what we call self-attention methods. So the fact that it captures both local and global relationships instantly. So, and I think that, it gives the model the ability to prioritize and weight different parts of the input based on the importance. Why we study vision transformer now? Okay, I think that there are two cumulative reasons. The first one is that PATs are replacing convolutional neural networks in cutting-edge AI systems. So we need to understand how they behave differently. And the second one is that bias in deep learning model is already a major ethical concern. So unlike text, and that's why we need to study, especially now that are transforming the field. And the second reason is that more domain-specific challenges and the fact that unlike text-based bias, image bias is more complex and it's harder to define because it involves abstract cultural and social factors. Okay, so for example, imagine a CEO wearing it is formal, it is informal. Okay, so bias is context dependent. Okay, so and this brings us to the main question of this work. So how do different models encode and propagate social biases? So what we started to do in my research group is to study this vision transformer. So we analyzed 10 different vision transformer to understand how they encode and propagate social bias. So our study focused on which layers of VITs encode bias, so for example, per layer or later decision-making layer. How different can these strategies, for example, contrastive generality and discriminative learning influence bias. In the third one, how bias propagate within VITs from representation to classification. And this is an overview of what they have done. So we created a balanced image data set. ImageNet is one of the EU benchmark dataset to VisionNet used, especially for training. So the subset was contained gender and attribute categories. And each image was face detected and normalized with a uniform preprocessing pipeline across all models. And this standardized data that was made of these methods are passed to our bias measurement bot that is called the IEAG. And I talk to you probably later in the next session. So what is this measure rate used? So this test is a implicit association test that was initially designed for psychology and cognitive tasks and then was adapted to the ECC. So it's an adaptation of the word embedded association test and is designed to measure implicit social bias in Asian workers. So it does not require classification, right? Because instead it examines how vision transformer internally organizes social concept in their embedding space. So this test quantifies how closely a Bayesian transformer associates target categories, for example, gender or ethnicity, with specific categories. And the attributes were already designed in the test and are fixed up career, family, or positive or negative association. So how this work? So we select two categories, for example, with male or female cases, and two adjective categories, for example, careers and family. So these categories are represented by chosen images that reflect these specific social assets. The second step is that we extract embeddings from the pre-trained vision transformer. So each image is fed into a pre-trained DATs, and then instead of asking the models to classify the image, we extract its internal representation from the last hidden layer. So why even did this? Because these embeddings contain information on how the visual transformer perceives the image. So we decided to use embeddings because bias is not just about classification, but is encoded in the way the model structure the knowledge itself. So we measure how close these embeddings of target images are to embeddings of the attribute images. And of course, negate this space. So if, for example, if male embeddings are closer to career and female embeddings, this suggests that there is a gender career bias. Higher positive similarities means that are stronger association between these concepts. And second step is that we measure the distance. So we compute the distance between target concept and attribute concepts. Attribute embeddings in the BATs. And of course, stronger association suggests a higher level of bias in our DVAT models structure social categories. And the third step is to quantify bias. So the score reflects how strongly a model associates certain attributes with social needs. So what we found is that there are different bias strengths across different BITs model. So bias is present across all BITs, and this also depends on the fact that we use ImageNet, that is a data set that is already proved on guides. Okay? But our idea was not to have a result that was completely free of bias, but instead to see how the model codify a bias, an image, a data set that is already biased, and to see if they amplify or not during in the embedded space. So the stranded impact, of course, depends on the model architecture and training paradigm. So some models amplify bias in their representation, while others, for example, show unweaker effects. And of course, this variation we notice that it's not random. So its creative and self-supervised models tends to amplify that sub-bias, particularly in the logic embeddings. So that is the stage where the models take the final decision. So this means that if the training data contains stereotypes, these models reinforce and even magnify those biases in their internal representation. And on the other hand, generative models exhibit human bias. So these models don't rely on predefined class labels or categories, but for example, and this in a way makes them less prone to replicate social bias from those dates. So because they learn in a more unsupervised or redistribution-based manner, I would say, they don't create strong associations between identity-related features and specific social constructs. So For example, this is one of the results that we got. On the left, you have the bad boy, and we had the male career and female family boys overall that. So on the right, we had the low kids, and those points form a much tighter male career versus female family cluster, especially for these two monads. And this indicates that bias define more at the classification level. For what concerns, for example, gender career bias, I think that the trend is similar to the previous. So the most of the division transformer encode the gender fit bias, big price, use those traits. Sunny PATs form tighter clusters where both decision and state effects. And this difference is due to how they encode relationships between concepts. For what concerns gender science, the trend is again similar but a bit different for what concerns this. So someone that's amplified scientific associations and they cluster representations of gender and science more 5D. So bias is observed more in internal feature representation and in final decision layer, and these reinforce learned associations. What we found is that in this case, generative models exhibit minimal bias, and this is likely due to weaker clustering of social constructs in their error space. So I would say that bias amplification in this case is more pronounced in models using contrastive or self-supervised learning strategies, while generative models tend to encode weaker bias, suggesting that they are less effective by training data stereotypes. And you can see that here we have lost the rights, and these show much tighter male science versus female either half clusters and forward on and lunar models compared to, for example, the background embedded up left. So I think that there are two takeaways of these studies. Vision transformers are quite fit and me need to step onward, especially because we are using them in different field and application. So the stimulative and contrastive self-supervised models in our study amplify stereotypes more strongly than is in the most image modeling generative models. Logic embedded for much tighter clusters, and thus exhibit more pronounced bias compared, for example, to background embedded. And planar embeddings may scatter noise, reflecting overall weaker vibes. I think that the last one is that association test that he used showed of course, self-bound demographic intersections, and even though especially stronger application. So I think I don't. Yeah, that's just.
Are there any questions from the audience? Yes.
Thank you for switch to help. The first is conclusion about supervised learning might lead to more aggregating bias. But if you know beforehand that is the case, can you introduce additional measures in the self-learning also optional there? Such that, in the learning, the critique, you can evaluate how good you are doing this even 2 months of retraining. Can you introduce additional measures to improve this supervised learning when they are trying to prevent possible bias? Okay.
I think it's an interesting question. We wanted concentrate on classification paths. So our idea is to concentrate on how the layer is already learned. I mean, in the way that the model embed knowledge from the data. So this is not a matter of classification; it's a matter of how the training paradigm actually force them to embed an information that can be biased or not. So our idea was to, this study has some implication, of course, because it achieves, for example, different data sets, so they can see how this works differently. But the idea wasn't to concentrate on classification, but instead to see how the training paradigm change the way they amplify or reuse bias in the way the information pass to the first layer for the last one. That is the classification layer, right? But we stop a layer before. So I'm completely sure that there could be probably methods to what you suggest. Not sure yet. So I also think that based on the models, you can, for example, use different methods to do what you suggest.
Thanks for coming to the session. Thanks for the outlet to invite me for the session. It's a communication of the outcome. There are several versions of the title. And then just also reflects my view of changes over time, how this privacy and fairness, they are two most important ethical concerns for algorithms, how they can enforce each other or contradict each other. At the end, I think I just settled out this interplay to take a more neutral stand on this. But just to be clear, if you look into the literature in computer science, also in the image processing domain, people tend to agree. There's also mathematical proof that fairness, that the privacy, they cannot be achieved at the same time. There's a impossibility theory saying that if you want to improve one, you could make the other worse. But then if you focus on this very specific topic of robot navigation, that's what I'm trying to do today, then there are some subtle. So it's not that this impossibility without then that clarifies everything. If you bring in extra layers, the foundation, there can be different conclusions. That's what I want to get across today. I'll also start with the smart large language models. Right now, everyone has been using this, feeding prompts. We also try to do some translations as I try to understand Greek science around the city. Summarizing different papers, course, it's Python for all teachers, giving homework to students. And then so also for content creation. So that's more or less people are using it in daily life, but as engineers, especially for people who are working on this autonomous robots domain, that also opens new possibilities and challenges. Because the definition of autonomy for robots, in a sense, you want them to behave like a human being. You can look around, that is the task for perception. They can try to remember things, when try to associate things and give them a map. They can localize, try to identify the landmarks, and then come their path, try to identify where they are, and then do the planning. That's very much like human decision-making process. And then they also have to decide which path to take in the end, going from the starting point to the destination to execute a task. So if you look at the 5 typical steps for such a autonomous task, in the past, a lot of time has been spent on training using large amount of data for robots to understand how can they perceive, localize, plan, navigate in the end, execute. But with the availability of large language models, you can just assume a lot of chains have been done in the cloud by those big tech. And then you don't have to go to the very beginning. I want to train my robot to do every step by associating data with certain decision-making or cognitive processes. So that's what I mean that by saying that having the availability of large language models like generative AI, it's really made a difference. It's open new domain, a paradigm for people who are working with autonomous robots. But just to me, very big topic. But for today's topic, I just focus on navigation. And also to see how privacy can be built into this large language model driven global navigation. Just to report to you some work we have done before in order to introduce this Faraday's idea later in the talk. So if we have a native robot, so then this is a so if you have this robot, because what we have there a lot, you can have camera and have the lidar, and then you can have all the sensors you want to install on the robot. And then what this robot see, but that's in the office environment, it is called a point cloud. So that's typically giving you the information about the distance on the machine. With camera on ETBE, you can have the camera and the DeX. All the information you can have. And then what's typically done in the navigation setting, you can also have some rough information about the robot, about the environment that can help the robot to do the task. In this case, I'm showing the example. You can have the top view. Story high level, not too much detail, but roughly speaking, you know first from the transferability, for which room is connected and which other by which column. Well, those are the big high level information. And then you can do this through learning, but if that's the supervised learning, you can also label certain places. For example, to the offices, then you see there's a cluster. So that's also topological view, not reflected to a geometric position, but then topologically, you can go from a geographical information map to a map like this. And then in graphical navigation, they start with this path planning, trying to look for the right path in this process. But with availability of large language models, from going from the top view to get topological view and into the path searching, you do need to do the training as well. So if you remember, maybe you have done this before, a lot of training has been spent on associated concepts. For example, if I see the glass on the table, and then there's a chair of this table, you have to train the robot to make association. It's more likely is to be in the conference room than to be in the bathroom. With this idea of seeing glass water table chair is to be in the conference room rather than the bathroom or some other places. That has to be have trained a bit to train the bigger that for your robot to learn about. But the large language model has already built in that. So if you tell the robot, now we found the video inputs possible, just give what you see in the top view or the files map, then automatically you don't have to train. The robot will figure out what's the likelihood because robot is in a corridor or in the office. And then this can also automatically generate passes and select passes. So that is the kind of say our light, but also is the clarifying because all those knowledge we have used to try to do the training and then do the decision making here not needed anymore. Just by using generative AI, we can do it for you. Well, that's a good bit. And then we also try to build in this privacy idea. That is a video language model. And then, so you can see there are two passes. So that's the starting location, that's the finishing location. We can either go from the right-hand side, this is a pass, but it's also a left-hand side, there's a left-hand path still. It's detour, but the difference between the two passes is that this shorter path has to go through this hallway. There's a lot of offices around. That's the class of offices. The other longer path, although the distance longer, but then it's much less crowded. So then there's a differences in how the environment are along these two paths. Then we know that the task is to deliver a document to the HR office. So potentially that is a confidential information there, and that this robot might want to avoid to bump into or try to get into too many people around. So those are kind of thinking we have as a human being. Although we didn't tell anything to this LLM that this is confidential or this is a privacy concern there, and then there's some other social context, social concern you have to think about. Those are how being placed in our human hand, human mind point, and then indeed that's also reflected in the planning of large language models. That in fact, it you just give information as a prompt, as I want to deliver a document to the HR office, and then the choice of route will most likely to go to path one, to go to this longer task. So that is telling us this a very interesting observation that the use of large language models in such navigation tasks, it can already embody certain thinking of human if there this paddle. The hidden message of confidential information about HR office and the document is already be considered in this automatically embedded in this large model height of neural navigation. So they were very excited in the beginning, but soon they realized, okay, this approach also inherited the potential fairnesses. Just to give this example, now you look at the robots in the middle, and then we have two few HR officers contemporary here, and then their office is located roughly the same distance to the robots. Yeah. Look at purely the location information, they are the same. But then we can have different attributes to those given the two person. Tom, by default, this is a male, and they also give attribute Tom 25 years old is Asian, and then Mary's female 55 years old is married. So those are, you can play with all the attributes that give to those two HR officers. And then just spontaneous could give the actual piece of information. Two offices, one is for Tom, one is for Mary. And you can still rewrite this as an algorithm. But then now with the task deliver this confidential document, but the content is about maternity. That was a personal need, but with a social context. Then what you observe is that was much more likely, 70% that is 30%, the document will be sent to Mary instead of Tom. That's to us is a big shock because we didn't embed everything into our searching. We only change the description. It's the advantage of using large models is that we can use natural language. You won't have to program all the attributes and anything into a special data format. You just use our daily language. I mean, to me, if I say use to Tom or it goes to Mary, I do have advice if I'm giving the input, but this LLM, they have to be aware that they can make a big difference when applying tax. You clear this point I want to make? And then they start to make us to look into this. So with similar paths, the only difference is the HR RGUs. This can lead to bias choice. But then you which way? Yeah, we so this they have deliverance documents or authenticity, and then they look into different attributes, right? The certificate of the nomination. Then if we just set Tom and Mary, but now we keep explicitly the male and then the female, and then the disparity grows even bigger. And potentially we don't know what happens there is a black box for us. We can only assume that gender can probably get people box to say there's a fantasy or this can be common experiences can associate with task alternatively. For the age, maybe older age can be associated with your experience in handling family information, and then the nationality might relate to culture depth than responders. It's only our guess. We didn't go into that too much depth yet, but they just show you that different attributes, they all have certain bias generated, although they might have different facts responses. Then next down, so we clearly see that there's advantage using large language spot or the type of generative AI in domain application. We also see clearly there is a fairness issue that is of concern. How can we do this by understand and scope out? And then you realize there are different versions of definition of fairness. This topic also mentioned with cosine as a possible metric for fairness. But then we look into literature, they don't feel that the current available definition can be readily applicable to other hats. So that's why we come up with definition for ourselves and then try to explain what they mean. Just to before I give the definition, I have to set up a model properly. So then there's a set of attributes. Those are God's necessity. For example, the location. Okay, it's just a feature in the environment, and then they do not lead to any postal bias. And then in comparison, those are also like to use is A rather than that are the set of attributes that can lead to sensitive issues such as gender in this case. And then there's the division. So U vehicles attributes Max and A, there will be a division to be made and another example for the root to be chosen. And then of course there is a probability distribution. We can think about how the non-sensitive and subjective attributes they relate to the division there, and then the markup boundary just one way that they are somehow having this hidden probability distribution. In fact, there's a conditional probability distribution. Conditional on making an X, third is a division U to be made. So what we have done differently than the literature is that we introduce a utility function, so that because we want to evaluate how fair or how good a decision is, and then we want to introduce utility function that reflects once a decision is made, what that mean for any participants for the past executor, and then that utility function is used in the end to evaluate fairness. So that definition. So you can already see that you want to compare A and A trie. So remember A that we join a sensitive attributes. So to look at two values of the sensitive attributes, and then with the same length sensitive attributes, and then condition on that, you try to look at what is the value of your utility function, and you take citation. By look at maximization, so look at all the possible differences in those outcome of your utility, and then take the maximum of the difference of disparity as your metric for fairness, so that they're taking the logarithm can really compare the differences. But just to give you some additional remark of the reason that we introduced G of U instead of U directly. So as this repeat this point again, if you look into the literature, most of, not all of them, are using U in such commutation. Just look at the decision in the end. But then we really want to introduce this utility function there. So then really we want to define the fairness as a disparity in utility instead of the outcome direct. And then L, so that's a metric, is non-negative. The reason is that we are maximized over all the combinations of A and A prime. We try to get largest maximum disparity. Of course, if you repeat A and A prime with the same, then there still be one the ratio and the get here. So that's the least you can do. If you don't do anything, just keep the same A and A prime, that give you 0. But whenever you do some actual work, can find bigger disparity, you will get a bigger value in that. So in other words, this magic is non-negative. And then so when the disparity grows, and then this L increases, in the logarithm that is an increasing function. So this is a monotone function, and then this reflects, in fact, it's the value of L increases reflects a loss of variance, or in other words, that indication of L variance. That's our definition. That clear to all? Just to bring this further, if that's clear to you already, so that if this definition look at, if you are look at the same non-sensitive attribute and you compare the sensitive attribute conductivity, you can also say, I don't care about non-sensitive attributes. I only care about sensitive attributes. Then can put the combination a bit different in how the conditional algorithms categorize. But and then of course you can different without that. And then in fact there's never in this count I will call this the above definition called a local fairness. G means that we are treating the G utility function. And then this lower called the global fairness because they are biased locally for the transplex, but the others is globally the more in the information about X. That's our definition. And as I said, there are the existing definitions. So if you're familiar with the literature on fairness, there's one called the delta equalizer. That's saying that so if you have two sensitive attributes, you look at the probability of the possible outcome, and then their difference tells you how fair a algorithm is. They are bound by delta, and then that is called the delta equalizer os. The other is called demographic graphic parity. That is similar to what we have talked about the local global concept. If you ignore the non-sensitive attributes and only look at sensitive attributes, you compare the possible differences, the probability of outcome, and that gives you delta demographic parity. So there I also give the reference you're curious about how the two definitions are defined, for example, original papers. But just to make a connection, so our local science definition is more related to equalized odds, and then our global fairness definition is more close to demographic parity. Just to make it clear, we can also prove that for our definition, we actually for the local fairness, it offers a upper bound for equalized odds, and then for our global fairness metric, it offers a upper bound for demographic parity, which also proves that the author never knows. And I don't want to detail, but in the math side, we are offering a much flexible way of looking into fairness because they're using a utility function. If you take the utility function to be the probability itself, do the any function thing, and then this reduce back to this equalized odds and then demographic hierarchy definition in the literature. So there was a connection to that. Okay, so that's our fairness story. Then come back to the private step because then fairness and accuracy they are mostly start in isolation. What's the advantage or what new insight can get in bring the two together? Just to remind you, for privacy, what people typically do, you have attributes. In other cases, you have sensitive and non-sensitive. If you go through a privacy filter, you're just adding in some noise to the system. And then those noisy version or in math version of the attributes go to a feedback maker and have to really see you have. By preserving or improving privacy, we mailing in add noise into the system. And then, so then privacy, you have this local differential privacy. For example, absolute the delta differential privacy. Right, speaking the case of delta goes to zero, that give you absolute differential privacy. It tells you that if you look at two signal x and x prime, can take x prime to be the noisy version of x, and then you look at the outcome of the algorithm of the two versions, non-noisy version, noisy version, and then the outcome of your algorithm should not be too different, otherwise you can distinguish it. Yeah. How different they are is evaluated by inequality, caveat the outpass. That's why it's called absolute differential primes. Just by applying this idea, we can also see that this to introduce this differentially private version of your non-sensitive attributes and differentially private version of your sensitive attribute. So we can introduce privacy also into this setup. But then what is interesting, so as it says remind you, there are already reductive impossible. There's an impossibility theorem telling that you cannot achieve privacy and fairness at the same time. That's what people generally accept. But I want to give you some subtlety for this argument. The idea is that you have to distinguish the sensitive and non-sensitive attributes when you are talking about privacy and fairness. If you are talking about the privacy of A, that is the sensitive attribute, then we have a proof. Just you can just think about by yourself. There are something sensitive. If I'm introducing noise to those sensitive attributes, then the algorithm will not be able to get access to the precise information and sensitive information. And of course, that will improve fairness, because then the less knowledge you know about the sensitive attributes, the probably more fair the sound is coming. So that's the draft idea. But the mathematics can prove that once you are introducing this privacy to the sensitive attributes, you can give a attribute for the fairness metric. When that is the same as this absolute. Remember, in the differential privacy, the smaller absolute becomes, the more private the algorithm becomes. But then this same absolute can be used as a attribute for the fairness. Our proof I will not go through. So what does it mean for our navigation? Yeah, so if you're introducing the noise of the sensitive attributes, in other words, you are making the sensitive attribute less and less accessible to the navigation algorithm, then if you know all the information about age, gender, and nationality of Mary and Tom, then this will more likely go to Mary. But then if you mask some information, now you only know the age and nationality, it's somehow the class distribution become more equalized. And then if you only know nationality, and this can even more equalized. And then that's very natural, just like checking our community script. If you are introducing noise into sensitive attributes, this can improve fairness. But what is more interesting is to look at products that are not sensitive attributes. There is also a mathematical result. It's not a technical, but the rough idea is still there is a upper bound that depends on also courtesy metric that can upper bound the fairness performance. So then ideally can we can look into this called the total variation that calculation have used in order to get blah 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 bad. But what that mean? So in this case, if you're adding noise to the non-sensitive attributes, then you're making the location information less accessible. You can mask your map, and so then all those objects are less visible now. And then because you don't know too much about the cloudiness in the environment anymore, and then those cover sequencer can be less well adjusted. But then you do not know where it's crowded, how to avoid people. And then as a result, the text is more equalized in this case. In other words, in this case, you are making the privacy consideration worse, but you are improving fairness. Actually, in this message, so there were maybe one was of your community. But then again, if you are looking at the part of the non-sensitive, sorry, I should go back. So yeah, I forgot to mention a big assumption in here is that the utility only depends on the non-sensitive part. Because in that case, you are only look at how far you're traveling, and then that utility function only depends on the location information, and not on the boundary information. But then if you allow it utility function to depend on both sensitive and non-sensitive information, and then the conclusion changes. So now instead of a upper bound, you can only get a lower end for your variables. Get their proof value below 2. But just to look at what this means, so if you are introducing mask again, the map, so you're making the location information private, but then because location information is not accessible anymore, it makes those sensitive attributes play a bigger role. Because LLM compared with running, and then they will pay more attention to those sensitive attributes because the non-sensitive attribute is not available or less available to them now. That is only make the fairness worse. So in this case, instead of you are improving fairness, you're actually making the fairness also worse. So then you are making both fairness and count of towing information become worse. So that's the other case. So you can see that it's kind of a complicated story, but the key message that I have trying to deliver is that so there are a lot of fairness issues in LM-based approach, and then so we have to just kind of strong assumption that you are able to separate sensitive and insensitive attributes clear at near the start over. This is already a developable path. But even with this strong assumption, you're able to distinguish sensitive and insensitive attributes. It's still open question. You have different utility functions, and they might depend on sensitive or non-sensitive attributes, but they will lead to totally different conclusion about fairness. Your platform will be vacant. There will work in that process. So I did some papers about the results and also deploy some of my two students who work basically on this project. Thank you.
Are there any cases? That's the problem. I UAG was a student, so I was wondering how actually LLMs can announce these stats fast. So why using LLMs to do something that can either probably something that is lower, you can have bomb control on it.
Yeah. So if we do not use LLM, for example, if we want to learn what is table, so this table looks more being conducted, but they are both states. So we have to spend months try to associate the shape color to the concept table. But give a task, you put the bottle onto the table. When the robot have to identify the table first in an unknown new environment, the table can take on a forms. So then the training is really trying to get a lot to know what can be a table before I can put something on the table. But with LLM there, and then if you give the image, you give the kind of label of the image, automatically kind of identify tables given. So then you to see all those data association part. That's one example why LLM can be more efficient in navigation.
So the reason is that because relevance in cross-bands keeps the perfect segmentation. Thank you, Cameron.
Yeah, I mentioned 5 fantastic that's upon the local practitioner card, but for planning part also. So if I try to get a task, in the old days, they have to do the semantic planning. So that's the target. So how can I identify a task? The not learning, and then can now also be done by my just can identify the task can go automatic. So in all the 5 steps I mentioned, perception, localization, planning, the navigation, the modification, each step, LLM can place both have out.
Doesn't enhancing privacy then generate the safety? Like if you plot in the map, then the router doesn't anymore worry spread, but it's not meaning the sensitive information is less protected.
Yeah. So of course that's category the introduce the ghost flashing voice, but that would mean anything but in that. But then because you are implementing knowing the privacy of engineer, then the type of mask you use will reflect the physical shaping of the system. In our example, we are masking off the postal structure of the ORs, but we leave the pathway, mouse paths. So that way they can still identify postal paths, but they don't know the information allow for that. Okay, thanks. That's
So you want to balance the privacy and the fairness. Would it be interesting to formulate this at a straight optimization problem where you say, okay, I want to reach this level of privacy and maximize fairness?
yeah. Thank you. A very exact point. That's why I introduce utility function. Because the utility becomes up to be optimization. But it's a very mathematical formulation here. You can free get its upper lower bounds or equal to left. But then I agree that is very useful approach. You probably go in that.
So you introduced the utility function, which helps you do a lot of things. So can that introduce unfairness? Because you're picking it that
Yeah, but then this is not utility function, just a abstract. They only require to be magnetic. You have zero at the fire condition, and then it's a monotone function where you don't have any other e-commerce specific. There are a lot of possible choices. I think it's already hijacked.
Okay, thank you.
Today I will talk about how does boundary transparency with combination gates. So we will explore several different settings of transparency, and we will explore how they influence the dynamics of combination gates. So I would like to utilize a very classic copying model which illustrates different settings of transparency. So we'll utilize this Uno. Suppose we are running each of us is running company, and we are competitors, and each company's action is to choose the quality of product to produce. So we need to product this square component with this figure, and after all of us determine our actions, the price of this product will be determined by the total supply. And then each company receives the post option GI of X, so which depends on its own action and also other option sections. But here, CI of XI is a production cost. So each of us is rational and is to minimize our own post option using feedback information from the market. And the feedback information would depend on the market transparency. So here, we will consider the market transparency being that it means the public accessibility of other companies' actions. For example, the market can be fully transparent, as shown in this figure, so each company can observe other companies' actions. And in this space, we can have some strategic behaviors. For example, even other companies' action, I can play the action that brings best response to the, or I can perform the fictitious play and other strategies. It's also likely that the market is not transparent at all. So in this case, we cannot observe other company actions, and maybe the only available information would be the cost evaluations, which is how much money it would earn every week. That's it. So in this case, how can we optimize our actions? Maybe we compare our cost function and this week compared to would be the last week cost. And if we find that by increasing the production level, we will get more money, then for the next week, it will be in increasing direction. So the market transparency depends on the available information of each company and plays a significant role in shaping companies' actions. And in this talk, we will consider 3 settings of market transparency. So the first setting is this no transparency setting. So in this case, each company cannot observe other companies' actions, which we cannot buy as minor phi, and they cannot compute the real information of other information. And the only available information would be the cost evaluations. So to clearly illustrate the available information of this have this new figure as shown on the right hand side. So each company needs to feed this action at I to the market, and market will return each region post action to each affiliate. And we'd also consider these 4 transparencies A. So as the name suggests, everything is available, and you can observe other companies' actions. And so each company can output actions using more information or some other spreadsheets. We also have this U figure to illustrate the available information. So after each company in their action to the market, and market will return other content action and also some green information. Besides, we also consider this asymmetric transparency setting, which is the main focus of this talk. So in this setting, we consider the case that there are certain companies that are very powerful. They can observe all companies' actions, but other companies cannot. So as shown in this figure, the powerful company would be company 3. It can observe the actions of company 1 and 2. But company 1 and 2 cannot observe other companies' actions. So examples of this kind of game could be games with leaders and followers, where the leader can observe the follower's action but not vice versa. And later I will show you that this asymmetric game can also be applied to some risk-averse games. Okay, so we will consider the 3 different settings, and we would like to answer this question: how does market transparency influence the dynamics of from major games? And to answer this question, we have to specify 2 blocks. And the first is what class of games we are considering. But there are so many kinds of games with specified class of games. And the second point is what kind of strategies the agents are using to obtain their actions. So we need to assume the agents are playing the games with some rational strategy, and otherwise, if the agent just randomly play the action and not analyze itself. So in this talk, we will focus on also combat speeds. So suppose we have 10 rational agents. So how we utilize technology agents instead of only. And they need to minimize their own construction in GI. If GI is convex in Xi for all the agents, then this thing is a convex phase. And here are some preliminary results. So Nash equivalent is a very commonly used motion in history. And a Nash equivalent X star is a point that satisfies this equality. So iteratively, at this Nash equilibrium point, each region has no incentive to update this function, to change this function. This is like a stable point. And as shown by this reference, there exists at least one Nash equilibrium class of cards. So we don't need to worry about resistance. We are also interested in this strongly monotone condition, which is explained by this equation. So strongly monotone condition is like a stronger condition. So in the single instance, it is equivalent to the strongly convex condition. So you can imagine that so strongly monotone games must be a common theme, and it's shown by the same reference that strongly monotone games have a unique Nash equilibrium. We can talk about Nash equilibrium conversions in ECCs. So as for the strategy, we will consider the breeding type strategy. So in other words, we assume that the agent will perform gradient descent. And specifically, that each iteration, each agent I can select the action phase, and after all the agents complete their action, they will receive the feedback information depending on the market transparency. It can be the cost of variation, it can be the breeding information. And then each agent performs gradient descent in your rational meter, be that the agent who prefer first order break information will be accessible and resort to zero order information, which is conjugate variation sample S. So as we go in convex compilation, the first order answer has a faster convergence rate than the zero sum vector. So in this sense, the first order gradient information is more valuable than zero for championship. As the edges are rationalistic, they will utilize the first order information in the test. And now we can specify our board, which is analyze the gradient type dynamic plus convex states and the different setting of high transparency. So let's start with this low transparency setting. We call that this setting. Each region I has no idea about observation inspections and has no idea about the first order gradient and has only access to its cost calculations. So each region relied on the zero order information complete with action for you. So in what follows, I will briefly introduce the 1 point zero scalar population. Suppose we are trying to estimate this gradient of shape and the point x. We need to do these 3 steps. The first step, we need to perturb the action x by delta u, where delta is a scope parameter with a scalar, and u is a random variable drawn from a unit sphere. And secondly, we need to query the function value at the perturbed action x hat. And thirdly, we can construct the gradient estimate as shown in this version. And here, the unique dimension of x. So it's shown that if we take expectation on this constructed gradient, it equals to the gradient of some smooth function f delta, and f delta is defined as the expectation of f of x plus delta v, where v is drawn from a unit point. So in theoretically, the constructed gradient is an unbiased estimate of a smooth function, and this smooth function f delta would be close to our original function f if it's like a small value of delta. So this is how the zeroth order of a population works. And now, inspired by this, we can have so each region will utilize the zeroth order of population update their actions, and the dynamics can be summarized when this step with a point. So for each time step t, each region I samples a random direction to it, and then they will pay the preferred action x hat it, which equals to x it plus delta times light. And after all the aging their actions, they will receive the cost evaluations and this action profile. And then they can construct the gradient estimate hetero GIK and then perform the projected gradient descent. So you might have noticed that this is a bit different from the traditional zeroth order foundation, because here our Kawasaki I depends on other region sections that x hat minus it, which is also a random diagonal action. But fortunately, we can show that if we take expectation on this gradient estimate, it still equals to a gradient of some smooth function to have delta t, and this gi delta t is defined as the expectation of something over both omega I and the u minus chi, and omega I is from the unit 4 and u minus I is from the unit sphere. So similarly, if we select a small value of delta t, you can expect that this gi delta t would be close to the original function gi. So, and then you can expect that we can have some convergence guarantee. And before the analysis of this full transparency setting, they make some standard assumptions. So in assumption 1, we assume that the cost function is bounded by u for each agent. And in assumption 2, we assume that the gradient of gi with respect to xi is the discontinuity kinds of all the agents. And we would analyze two performance metrics. So one is the reward for agent life. So reward is a commonly notion in online operations. So it is the specifically given the action sequence generated by some algorithm. It is defined as follows. So basically it is a difference between your actual performance and the performance of the single best action equation. And hopefully this reward be sub here in T, where T is lux of the total balance. And the other performance metric is natural equivalent convergence, which is the difference between hex T and X star. X star is a natural equivalent. To note that the reward is an individual performance metric, and the natural equivalent convergence is a group level. Okay, so now we can present our results. Let assumptions go, and by appropriately select the parameters, then this dual transparent we can achieve sub-binary weight. And if additionally this thing is slightly more coded, then show the natural equivalent convergence. So these results are not you. There are some existing results, and the existing result do not show the impact of the number of agent n on the traverse tree. And we show it here because Bollinger we will use it for some details. And let's move on to I will omit all the proof duplicate and constant. So let's move on to the full transparency setting. So in this full transparency, in this setting, each agent can observe other agents' actions, and so they will perform the projected gradient descent using the first order information. And the algorithm is summarized, the dynamic is summarized in this algorithm. And for the analysis of this set is due assumption. So we assume that this JIX is discontinuous with X for all the agents. And if this assumption holds, then we can show that actual 2 achieve some binary weight. And if the being is additionally strong monopone, then we can also show a natural equivalent emerges. So you can observe that this full transparency setting has a faster convergence rate compared to the no transparency setting. This is because we have more information with full transparency setting, so it is expected. And let's move on to this asymmetric transparency setting. So recall that in this setting we have two groups of agents. One group of agents has only access to the cost derivations, and let's call it these agents the zeroth order agents, I think. And we assumed the number of zeroth order agents being span Z. And the other group of agents can access the first order gradient information. I will call them the first order agents. The dynamics of this asymmetric game can be summarized in algorithm 3. So for each time step T, when agents play their actions, the zeroth order agents IZ will sample a random direction U and T and play the perturb action, where we need to utilize the zeroth order operation to undo their action. While the first order agents IF just play an original action text by FD. And when agents receive information, the zeroth order agents obtains the cost evaluation GIZ and the action profile X hat 3D and X hat T. While the first order agents obtain this first order information at this action profile. And then they can perform the projective gradient descent based on their own gradient estimates. So we can observe that for the zeroth order agents, they obtain the cost evaluations at the point X hat T, which is not a random action made by the first order agents. So the first order agents introduce some misalignment to zeroth order agents. From another perspective, for the first order agents, they obtain the gradient information at the point X hat T, which is a random action verify the zeros order agent. So the zeros order agents introduce some randomness to the first order agents. And despite this intertwined dynamics, we can still show the emergence in the path of convex waves. Yeah, I will omit the technical details, but so that these assumptions hold by appropriately selecting these parameters and this asymmetric arc zone, couching subbinary wave for both the zeros order agent and first order agents. And we can observe that the orders of T match the results to pure first and zeros order cases. But the regret of the zeros order agents has a slower constant compared to the pure zeros order method, because here pure zeros order method, it relies on the number of agents there, while in the asymmetric case it relies on the number of zeros order agents density, and density is always less than or equal to 10. So it means that the existence of first order agents in asymmetric case help accelerate back emergence of the zeros order digits. And given that the being is 21 at all, we can also show the natural period emergence. So if we observe this result, if we set NZ of n, it means that all the agents are there for the agents. This result matches the no transparency result. And if we set NZ0, means that all the agents are first order agents, and it matches the full transparency result. So and otherwise, it always lies between these two indices. So these observations show that our asymmetry result is more general and includes these two extreme cases as special cases.
And we have done some experiments on an asymmetrical case. So in the left figure, we plot the individual regret for each region.
So all that we hope the regret is moderate as possible. We observe that the zeros order agents has a larger regret compared to the first bucket boost. And in the right figure, we thought the difference between xi and xi star. Xi star is the bias component of natural variables. So we hope it to be small as possible. And we observe that the zeros order agents has a slower convergence rate compared to the first abundant agents. So these two results show that from an individual level perspective, the asymmetric transparency introduces some unfairness among agents because the zeros order agents emerges faster. But from the group level perspective, we have tested the natural convergence for different values of NZ. NZ is the number of zeros order agents. We observe that if we increase the value of NZ, so we have more zeros combinations, the convergence rate becomes slower and becomes finally very close to the purely and zeros method. So it means that so from another perspective, if you have more first order agents, you will have faster rates. So although the asymmetric setting introduced unfairness, but from a group level perspective, the first order agent help accelerate the overall properties. So in what follows, I would like to discuss this asymmetric transparency with overstains, because the asymmetric transparency can arise from agents' aversion to risk for which the graded information is not accessible. I would like to utilize a conditional versus risk CFR is high time. The CFR is a commonly used risk factor in healthcare and diplomatic applications. So it's defined as suppose we have a random cost Z. So this figure clause is probability as the function for Z. And even the risk level R but be for Y. So it means that CFR we are interested in the worst % of this random quantity. So suppose we the area of this free region is from 1, and we are interested in the probabilities of this correction. And So we have another risk matter value at risk. So value at risk is defined as the 1 minus alpha on type the distribution, which is represented by this vertical rate h pi. And even this bar value, we see bar value is simply the expectation of play conditional on C is greater than the is bar. So basically, we are computing the average of at the right hand side of this spread one. And usually the C4 is the average of the worst power values. So we can care about the worst is. So, and if we set alpha to 1, and he mentioned that we care about the 4 provider that the C4 just reduced to the expected yes. But C4 is a favorable risk measure, but its Boolean is usually not accessible. So let's consider this risk averse game, where each agent takes to minimize the Ci function, and Ci function is defined as C var alpha I of this surpassing positive I, and relatives of Gi comes from the random variable let's say, and the C is used to represent exerted R. So Ri comes from 0. The value of I is from 0 to 1. If so, we assume there are some risk averse agents, and their alpha I is less than 1, and also some risk neutral agents, their alpha I equals to 1. So in this case, we have two groups of agents. For the risk averse agents with alpha I less than 1, the Boolean information is not available because not on we are support. So these agents will rely on the zero-score answer, which from the function evaluations to update actions. While for the risk neutral agents, is alpha input 1 in the compute. We easy to compute with Boolean because the CIX this is a expectation of pi. So this agent will utilize the first order Boolean information. And so for this risk reverse case, with both risk reverse and risk neutral agent, we can apply our asymmetric error, and we can show that our asymmetric error converge faster than the pure dual SRG. The existing without using purely dual organizer for whiskers things. Yeah, so I think we are now finished all the stuff. So in summary, so we have baseboard. We have showed that convergence rate of gradient type dynamics, they have cost of probability, and we'll show that all of these settings, the dynamics of this setting will converge. And the convergence rate of the asymmetric transparency always lies between the full transparency setting and low transparency setting. And our asymmetric algorithm is more general, because the purely first and dual order methods as special exist. And we also observe that this asymmetric transparency, intuitions, and fairness, the first correlation can help accelerate the overall. So some future works would be like including more types of strategy or agents. For example, the agents can play the best response, or they can perform the fictitious play within some other strategies. And it's also we are also interested in consider all class of days, for example, to be non-convex day, zero-sum comparable. And I only call the proof, but if you by the choose some proof, we present these filters. Yeah, and that's all.
Any questions?
Thank you for interesting help. Could we notice this idea that first order agents have accelerates of convergence with asymmetric case? But we also know that this gradient type dynamic might be sensitive to perturbation or rapid measure bleeding. So do you encounter cases in the mixed combination of first order operations? Then the magnetic oscillation near the equilibrium, so converges at the given fact and your.
Yeah, thanks for the good question. So, from my coding experiences, I have not encountered some like vague oscillations because I think because the reason is we focus on the convex, which is like a class of things with boot purpose. So I don't say like big oscillations.
Yes.
Follow-up question here. On your last two questions, you also extend your results to non-convex shapes. Any ideas there how to extend this work? But then let us see you want to just share.
Yeah, thanks for the good question. So I think the analysis of non-convex is actually very challenging because for example, the fundamental problem would be like we cannot guarantee even the existence of such grid. So, and then you have to determine what performance metric you will use, right? For example, you can compute the norm of gradient in single agent case, but in non-convex states, maybe that is not a good choice. So, yeah, so for non-convex things, people have analyzed some other class of things like you can feel a zero sum or some another class of things like yeah, I guess we need more perceptions or for issues.
Because I've observed that the bias downward is that if that were pictures and one application which report that some critical studies that we're gonna read here too is the interlink ranking. So a lot of you now will search, go on Google, you search for a query, you get some results, and people have observed that you look at a different demographic area that are presenting your search results, you might see some discrepancies. And that may reflect something not seen in society, but something the subbasic is worse than that. So study from I believe targeted gate look at the representation of women in Google search results when you search for CEOs, women in the US. In the US, there's about 15% of women CEOs at the pie, but if you look at the photo search results on the first page, you only get to see about 11%, which gives them a sense that there's something going on related to the pureness of representations of first that don't really match even the reality. People followed up on that to try to understand what happens why you decide minorities or sensitive groups get pushed down in a ranking, and they've noticed that in more recent studies as well. This comes from a psychology study actually, where but they did a study on Google search. They basically put a general digital query on the Google search, and they measured the percentage of different brackets, men and women, again in the image search results, and they correlated your investigation with the gender gap index from the location in which the Google search result was that. So for more unequal countries, you would see like lower representation of women for very neutral terms, such as like person or other things. Whereas for more equal countries, you see that case, which again give them a sense of like, okay, these search algorithms maybe mirror and sometimes amplify the differences we see at the different groups in the different societies. So there's some personalization, there's some mirroring of bias, and maybe some amplification of bias. And what we know is that these algorithms use network features. So what our work is interested in, just understanding how exactly do these network features play a role into the how these algorithms work. So some of the most common algorithms that are the foundation of search in naked analysis and what you see right now in Google is page rank and closely equal to blank hits. I'll describe quickly how they work, but they basically use the network structure to create a relevancy hierarchy, a relevancy hierarchy for search edges, where the different websites are the labels and then now, and different links are the the different edges that go between them into a way that forms a network. So basically, the more popular websites are the ones that show more higher up in your search results. They're not just more popular, they're more relevant, which is decided by some central metric that combines an emerging variation. So in these kind of networks, it really matters, particularly lines, it matters how well you're connected, how well your website or known or whatever it is, you as a person that exists in this embedded graph is connected to other people, but also who you are connected to. So if you're connected to more popular people, maybe you have a better chance showing up higher in this dramatic state. So we can generally, well, what we're to abstract about this is thinking about it in the following way. Let's say you have two groups. All they know them, these are the different doubles. And the colors represent different groups. For example, men and women, as we saw before. There's edges between them that may represent some sort of relationship, informational, social, and so on. And initially, you can look at the network and say like, well, if I rank them by their degree, that just means more popular people are at the top. And I can see that way what is some form of representation if I look at who's the most popular. Right, there's multiple nodes, right, but there's some random nodes. If I look at the top K ranked by degree. What happens when you apply one of these ranking algorithms is that everyone gets some sort of centrality metric, you rank it by that score, and then the top whatever results will show up on your Google page. So we're interested to see how the representation of the different ways changes if you look at the network itself, for example, the embedded rank, as opposed to the ranking when you look at what is the people search. What is the ranking resulting by page rank kids and the black algorithms. So, and very well we saw that, well, one of the groups maybe like shows up lower than my QLiggins. And I'll show you how that shows up in our practical results as well as theory. So how do these algorithms work? Maybe I'm sure a lot of you are familiar with PageRank on Google search. It basically creates a score embedded in the vector x at each type step. It does an iterative process in which with some probability eta, it does a random walk through the network. These a transition probability that you would define based on some network G, the adjacency, and then you just hop based on your basically count of friends. And with some probability 1 minus eta, you would do a restart. The reason you do the restart is that this is a directed network. So in undirected networks, you just keep doing the random walk, you'll end up with the degree distribution as the degree is a stationary distribution. With directed networks, that didn't really work. You don't end up with some stationary distribution. But if you do a restart, and you start at some random vector b, maybe it's a uniform one, in personalized page rank, it's not a uniform one, and you really bet on your preferences as well, then you do end up with a stationary distribution, and that is, if you let this process run at equilibrium, you end up with a matrix centrality. You rank your nodes by this centrality, and that's your ranking. The nodes that show up higher would be the ones with higher startup costs. This is also equivalent to counting forward paths in your network. So the way people have studied and the way we do it and studied how PageRank affects on or how we do this neutrality is by simulating some forward paths and then computing what the number of forward paths in which end up in every single hub. And that is equivalent to computing your PageRank distribution as well. Similarly, so I don't know if some of you might also know HITS. It was developed at the same time. PageRank took off in the Google search. HITS took off in some search engines, don't count as much. It's a very related algorithm, and there's something interesting about it that it's very different, but yet similar to PageRank. So instead of doing the 4 paths, I'll show you actually deduct the 4 paths. But it is equivalent to saying, well, I don't only care about like how many guys end up in a 4 path. I'm going to assign an authority score to each node U, the time equals katam key, and the hub score. So every time the authority of my node is basically the sum of my hubs. The more nodes point to me, the more websites point to me, the more important I am. I care about who points to me, can't just like be random people. Similarly, I'm a hub if I'm pointing to a lot of nodes. So I'm a good hub if I'm pointing to a lot of good authorities. I'm a good authority. I have a good authority score. If a lot of hubs and good hubs point to me. And if you run this process, this is iterative process, you end up with the principal I detectors of a matrix that is basically the adjacency matrix of your network transposed within itself. This is also equivalent to just running forward-backward paths. It's basically saying I would start from a node, I go to a hub, or I'm trying to go to a hub, and then I'm going to an authority and so on. So you can see how these two algorithms are similar in the way they compute centrality or method. They're also slightly different because the init restarts matter more. You want to accept that, yeah. So in our work, we are basically trying to understand how network features provide some evidence what bias is amplified or deviated in these kind of algorithms by using the way they use this the task coordination by the center centrality in the stationary distribution. So here's what happened on the real data that we analyzed. We started with some networks. One of the networks is this data collected from the American Physics Society. The notes are papers, and the paper link to it links to each other whenever they cite another paper. There's two groups, two subfields of physics, classical mechanics, quantum mechanics, I believe. And they're pretty separated, right? So you're not really going to cite quantum mechanics, you do classical and vice versa. So they're pretty segregated groups. You can think as very, very homophilic in a way, given in network theory. So what we're plotting here is on the x-axis in the top X% of the nodes. And on the y-axis, this is representation of a minority group, one of the bit smaller, in the top X%. So it's an equivalent of looking at the graph that's on the left side and moving the threshold of your ranking further up as you move to the right. For example, if you look at the top 1% of nodes, and if you rank the different colors are different ranking Cs, if you rank them by degree, you will see that at around 1% you get, in the top 1% of nodes, you get about 20% minority. The dashed line is the general minority representation. So they're kind of underrepresented from 30% to 8. If you rank them by the track, then you're a little bit better actually. So because it's like, oh, it actually improves the minority representation. Whereas if you rank them by hits, the minority representation just like drops to 0. Not only for the 0%, but you can quickly see how it drops to 0 as you move further up on the ranking pretty quickly. Already at top percent, it's the top 10%. It's really low. Interrupting, you have questions. Similarly, we look at different data sets with slightly different behavior. So DBLP data, this is also a network in which nodes are, DBLP is this website of computer science papers where you have authors and all the papers here, right? So we made a network where the nodes are people and the connections are their citation. There's a paper of this person cites another paper of another person. There's two groups, men and women, and they're much more integrated. There's about 22% women in this data set. There's about 500,000 people overall in this, 100,000 people in this data set. But they're pretty integrated, everyone has citing, right? So what you see here is that the representation of minority, I'm calling it R from red, state minority, in the top one, and in the top X% of the ranking is kind of the same for everyone. It's still far from the representation of women in the data set, which is about 22%. But all algorithms kind of mirror whatever happens in the degree distribution. And finally, we look at this other data set. It's a data set from Instagram, where those are people again. Their connections are whether they liked or commented on each other's photos. It's about abominated people, and it gets to groups, men and women. It's not really representative like Instagram. It's just the data that we collected through some process. There's about 45% men in this data set, and they actually have pretty high rate. So if you rank them by degree, they're pretty well represented in the very top. And you can see, and here it's kind of like moderately homophilic in the sense of like one group connects more with its own, the other group more with its own, but there are some interconnections as well. And what you can see is that, well, Gauge kind of improves the representation of the other group a little bit. It brings it closer to the space sign, whereas it makes it worse. So it amplifies whatever is happening in the network. This is all giving you a picture of how different networks may look like under these different ranking algorithms, and to say that, well, they look different, but what's the common point to them, and the main thing that we discovered is how exactly that this network structure can predict the behavior of these algorithms. So we're using network models to explain this behavior in PageRank and hits. In our work, we're trying to find like what exactly is, what's the ability when bias gets amplified or defeated. So first of all, we find that inequality in degree distribution gives to some bias in the ranking algorithms. Of course, part of like it knows benefit from like a popularity bias. But second of all, an important one is among the more communities. So we saw in this empirical data set at the high level that it can alleviate bias for PageRank. It actually improves the representation of some minority groups, whereas it can amplify bias for hits. And we formalize this using network models as a mechanism for explaining this kind of behavior. So I'll give you a short sense of what kind of models and techniques we use for this. We adapted a model, followed like a bias preferential catchment model from Avinet all to 2015. And these models were nice. It has two rows. Let's say we have do and fruit nodes, and it's an evolving model. So at every time the email comes in, it takes a color. There's a probability of being in the minority, of being red. And the node that comes in connects to nodes according to preferential attachment. So it traces which can reach verified. The nodes that are already connected, they get a higher chance to receive new connections as well. This preferential attachment leads to very skewed degree distribution, which people have observed more or less in online communities to lead to this power law degree distribution. Mostly, it comes with this original model, the preferential attachment model, proposed to explain some of this online networks as well. And the last ingredient, which is really important in this model, is so if there's different labels, red versus blue, then the connection is accepted only with a certain probability. This by changing the probability row between 0 and 1, you can transition from very segregated networks to very integrated networks, which is your basic preferential attachment model. So this model has a few properties. One of them has it presents inequality the degree distribution of these two communities. We know that the original preferential attachment follows a power law degree distribution. This model also follows a power law degree distribution. It follows two power laws, one for the red nodes and one for the blue nodes, with two different coefficients. And the fact that these are different means that the coefficient for the red and for the blue are different, means that when you look at the ranking by degree, the fraction of minority would basically vanish. Because you're looking at, let's say you're looking at top K nodes, the probability of having a top blue node in the top K over the number of nodes that are red in the top K would basically calculate that it goes to 0. The rhythm or blue would go to 0 as your network evolves and the number of nodes decreases. This is something we noticed in first of all, like the degree distribution, that a minority is underrepresented often. So in our work, let me give you a quick sense of what happens hits. PageRank is overstudied, and I'm going to give you a sense of how it compares to PageRank as well. But at a high level, this is what's going on. If you take a network generated from this model with preferential attachment, homology, and this majority-minority partition, the average authority score, this is the score you'll use to rank nodes under hits, for the minority nodes is going to be lower than majority. This is just a mean-code analysis. But second of all, you can find a close form relationship between homophily and bias identification, which tell the paper for the technical details, but a high-level point is the following. When homophily is low and the network is very integrated, the representation of minority actually gets better. The bias gets mirrored or reduced. In moderate cases, which are a lot of these online communities that we see some moderate homophily, bias is mostly slightly amplified, whereas when you get to more and more segregated networks, like you saw with the first network, with this citation network from physics, is then you end up with a very large bias identification against the minority group. This is what we saw in the empirical data as well. The ABS data set, very homophily. The EDP data set is high, moderately so, whereas the Instagram data set is quite, the DBOP data is very integrated, and the Instagram data is kind of in between. So you see this kind of transition in BP. So, what is different from previous work is that, well, until now, we knew about hits, that they had some empirical evidence, the not really theoretical, that only it hits very badly only in completely disconnected communities. We didn't know what happens exactly when it's slightly connected. So this this continuous relationship between homophily, the network structure, and keys is something we find rather subtle. We do find that, of course, the inequality degree distribution is the highest predictor for primary bias, either ranking out right as this one. And we've seen that over time. What about Baytrack? So Baytrack, so kind of a little bit more hopeful. We're doing we have some work on that as well, the paper that I already mentioned. But some exciting recent work showed that, well, if you compute the Baytrack distribution in preferential attachment networks, this was a conjecture until like 2 years ago, basically, to say that, well, if I have a power law, Gibber distribution will have a power law in the credit triangle as well. We didn't know. It kind of assumes so. We now know that it is a power law. It's just a heavier tail than the degree distribution. Basically, following up on that, it showed that recent work also shows that the Baytrack stationary distribution is complete if you have these two communities, red and blue, and preferential that for this we saw before, actually has the same coefficient. It has different constants, case in which we see in the empirical work, not only in ours, but also in other related work, that you still end up with some bias, but in some cases it does improve the representation of minorities among the rat. So in our proposals, you showed that through some equal analysis, we find the amount of bias that you see on average that gets carried through the constant itself, and then even if the power law is the same, but it's a force like less strong than having a distributional result where you would have different power law coefficients. Further on, so what do you do from here on? What do you do to improve this kind of bias? On the Baytrack side, some recent work shows that what you can try to intervene on the network structure itself to improve the fairness stand using Baytrack by trying to create links that first of all improve the network structure in order for Baytrack to act better as well. You can do that for Gits too. I would say it is like kind of pre-processing your data equivalent. On the vision directions, and we worked a little bit on this, and you can see in our paper, we want to characterize bias up to the constants as well. And further on, like to see like, well, what can you do? What other elements can you in the real design through the network itself, looking on the output in order to make this a little bit fairer. So one of the things you could do is try to report what happens from Baytrack. So Baytrack has this randomization, right? Like at some point you either follow a random walk or you restart with a random probability, which means that you randomize. And that helps a lot, of course. If you randomize everything is fair, but it also completely not relevant for what your search result is. Can you do something in the middle? Baytrack finds itself in the middle. You can do a single A with keys and do a B-star probability. And if you do that, well, yeah, it will basically follow the degree distribution that you see in the bias differential attachment model as well. So it does really well, and you can do that. A second question, if I found interesting, we don't really have theory practice. I would love to continue to work on this at some point, is to say like, well, what happens if you use more than one component in your network embed? So hits basically use the first component of the adjacency matrix transposed with results. Right? It's just the principal eigenvector, and that principal eigenvector score creates the ranking that you see it gets. If you use more than that, some are like all empirical evidence show that, well, maybe you can do better if you try a couple of them. So what would you do if you do that? You would basically say, well, take a function of the eigenvalues and take your basis record together with your eigenvectors. If you just use the first, so if A equals 1, you end up, and it is hidden, and you would just end up with hits. But if you try to span the subspace induced by this matrix, then maybe you can use more information that's embedded in the lower dimensions of the space as well. You can use many variant for this function, an entity square or some version if you delete this coding information tag analysis. Going over this rather. But I wanted to say that we find that in practice, it's really hard to find a clear result, like what dimensions should you use and how you should put them together. It really matters a lot on how many dimensions did you use first of all. And I'll show you quickly empirically what that looks like. So more than one eigenvector. It's basically a little bit of a mess, but again, the different colors are using different number of dimensions. And sure, at some point, the point is that we're trying to get to this baseline of proportional representation. It's not necessarily the best baseline, but it's one baseline to look at. So if you use different number of dimensions, maybe you're doing all the same in which the bias just like gets pretty bad and you end up with no minority representation. If you use others, maybe you're doing a little bit better. You're basically reproducing more or less the version of page rank, but sample actually a little bit better. Exactly how to do this formally, you found to be still open. This is for different data sets, but I think I'd rather leave a few moments for questions and come to bulky 3 directions more broadly. One of them is that how do we mitigate bias through network interventions? This also comes from like, well, you kind of have to combine some network recommendation with information retrieval, with ranking. I don't know how to do that without like Mike an actual experiment on website, but maybe you'll have thoughts. But secondary, you can think about like how do you make these adjustments to the random walk itself or to the way we implement these algorithms. Anonymization is one, saying a larger subspace is another one. Clearly there's other ways. And second of all, these ranking algorithms have impact on the content that we see or it gets recommended, but also people have shown it has an impact, of course, on like hiring effect, on the market share that Udo against there's a current antitrust case against Udo defending on their preferential ranking for their own products. So trying to analyze the effect of this ranking on the different stakeholders and the fairness associated in this larger market space, I think is an interesting direction. And of course, to generalize perhaps different network models. What we use here is basically it's preferential transfer models. I really like to use because they have some abstract properties and you can use some continuous time branching processes in order to analyze the distribution at equilibrium. But it'd be nice to see in other models as well. So let me stop here and take questions. Thank you, Uzas Orha.
Any question?
Just to understand your definition of homophily, but that's always the binary concept. So then there's only one label.
Oh no, it's a continuous definition. So it basically tells you. Let me get to this. Yeah. So this is the homophily here is defined as a probability of connecting the people of different groups. So if homophily, let's say, is 0, then you end up with a blue room and a red room and they're totally segregated. If homophily is 1, then they're totally integrated. If it's somewhere in between, then it can just be like a new node comes in, it connects with according to, it tries to connect according to preferential attachment. Let's say it's red, but if the other node is blue, it only accepts it with the probability of homophily. So maybe 0.5, 0.7, 0.8, and so on.
I meant there are 2 latents, but can you handle all the latents?
Oh, yeah. It's a very easy generalization from 2 nodes to multiple heads. Okay. You end up with different degree distributions where the power law just depends on the fraction R and this.
So those 2 are my 2 cats, Kimi and Kif. And of course, because they were really nice, when our friends were coming over, then they all wanted to pet the cats, hug the cats at home. And Kiwi was quite smart straight away. She just said, nah, I'm not really like the type of cat who wants to sit still. And because of this, everybody just learned this and let her. It was sort of making her a reputation. However, Keith quickly realized that this means that he's the one who will get all the hugs and the petting. And this is fine when there are only a few friends coming over, but when there are lots of them, he's not as happy anymore. Now, Keith is really cute and he didn't do anything about this, but he were a gay theoretician, rational agent, and he will perhaps very quickly realize that maybe he should also pretend that he is not really good at sitting still. And in that case, maybe he will receive less of the hug and the burden will fall more equally between my two cats. Now, with the two cats, this is not really a problem. He doesn't really mind. Not all of our friends knows about Kiwi's reputation, so everything is fair, I can assure you of that. But there are also some settings where this is not the case, and this is what I'm going to talk about today. I am more precisely going to talk about two-sided matching markets. And this is a work that I've done back when I was at the University of Zurich together with Aniko Hana, Kenny Joseph, and Ecologer. Very quickly, what do I mean by a two-sided matching market? We have several types of market where we have two sides that want to be matched to each other. Examples include schools and students, locations and refugees, employers and employees, and courses and students that want to participate in taking those courses. In all those examples and many others, there are two types of markets where we have two types of agents. Some of them are arbitrary. Every year we have the same schools, the same locations, more or less the same courses and employers. But on the other hand, there is one side of the market that is new every time. We have new students that want to be matched to the schools, new refugees coming to the national relations. For simplicity in this talk, I will focus on the first type of examples, about school trade, which is the classical one where we talk about two-sided matching markets. So we have students and schools. But keep in mind that this talk will extend to many other voices. So in such markets, we have two types of mechanisms. The first one is the matching mechanism. So everybody submits their preferences. The students say which school they prefer more. The schools say more or less which students they prefer more, up to one last colleagues, which I'll go back to. The problem is that it's very, very hard for students to form preferences. If I am a middle schooler that just finishes up, and I have a long list of high schools, if we think about big cities, it is very hard for me to know which high school will be best for me. I have to consider all of things. I have to consider the courses, the teachers, and all of those is very hard to assess without experiment. This is why there is a huge line of prior work that thinks about how to make decision support systems that can help students form their preferences. For example, there could be a recommender system that looks at prior outcomes, SAT results, baccalaureate exams of other students, and they try to predict what would be the outcome, my result, if I were to attend the courses of that high school. Now, those two obviously happen together in the same market, but often they are analyzed separately. If we think about matching markets, we can think what is often analyzed there is strategy proof. Do students have an incentive to misrecord their preferences? Do I have an incentive as a student to lie about my preferences? Or stability. After being matched, do I want to change the school that I assigned to, and will the school agree? If we think about machine learning-based forecasting, we think about poisoning and evasion attacks, which are basically ways of misreporting the data that is true. But those two were not analyzed together. And the question that we're asking here is whether there is a new type of strategic behavior that lies at the intersection of those two mechanisms. To do this, we go to a formal model, where we model each of those mechanisms, first of all, separately and then together. If we think about the matching mechanism, we have, again, the two sides of the markets. First of all, we have the students that have preferences over the schools. So for instance, the student 1 believes that school A and B are more or less the same, while student 2 prefers school A or school. The returning side also has some preferences. For instance, here both school would prefer student 1 over student 2. And then the matching mechanism takes this information into account and then produces a matching, which is basically saying which student will go to which school. Student 1 will go to B, 2 will go to A. In order to form these preferences, as I said, there is a forecasting procedure. So this would be a model that for every pair of students at school will give a predicted outcome. For instance, the SAT result of that students, the maximum number of points that they would get after finishing those kind of high school. Most of the analysis stops here, but there is one box that is missing. Because after the student and schools are matched to each other, the student actually goes and attends the courses of the school. So there is also an interacting phase where, for instance, student 1 goes to school B, they have the maximum outcome as predicted here, while student 2 goes to school A and they have an outcome of 19. This creates a history of outcomes that is fitted into a machine learning algorithm in order to play the machine learning model there. And if we put our game theoretic lenses now, there is also some utility. So depending on what the school does, for instance, give extracurricular preparation for the student or not, invest a bit more and help the student integrate, that they can have some utility. For instance, maybe student 1 doesn't need extracurricular preparation. The utility is the value, so it was 100 for school B, while school A maybe needs to invest in extracurricular preparation for student 2, and then their outcome, their utility is the value minus our cost and is actually low. This feedback loop is programmatic, and I will quickly explain why. If I am school A and I am allocated a student that is underperforming and needs extracurricular preparation, what I can do is not help the student that I'm allocated now. This will lower my utility now, but it will train the machine learning algorithm to predict lower outcomes for such students in the future. This will mean that I will lower my chance to receive such students in the future. This is different from a classical machine learning adversarial attack. Because I'm not misreporting my data, I create different interactions and create different data by changing my interactions with students. What we call those types of attacks adversarial interactions attacks. They are interactions which deviate from the one-step optimal interactions in order to trigger different recommendations in the future and change future predictions. If we look at the expected discounted utility, so from a mathematical formulation, can have the utility of this. We have the utility of spool Y if they are matched with somebody at type T, is the maximum over all the outcomes they would have if or on this for curricular preparation of their utility with that outcome now, plus the utility, the expected utility at the starting from the next time step, even that they added this outcome in the history of interaction is counted by some factor. That is a small bracket. What is important about this adversarial interaction attack? The first one is the level of attack. This is the magnitude of the deviation. How much does the spool deviate from helping the student the most that they could? And if this level is 0, then we are happy. Our system is interaction proof. But otherwise, we are not that happy because it means that there is some strategized going on. We gather so far the intuition that perhaps the schools really do have an incentive to interact strategically. But the question that we ask now is where this is the case. Is this always the case? Is this always a problem? Should we worry about? To do this, to answer this question, we done two things. The first one is to create an economic model and then do a game theoretic analysis on top of this to see what are the incentives in the simplified model. The other one is go to simulations, and this allows us to consider more scenarios and, of course, some that are more realistic and tailored to real data. I will make now a quick parenthesis to explain the economic model in the simplified setting, and then I will come back to explain the higher level results. So I will go quickly to this. I hope it's okay, but otherwise I will explain everything, all the big ways will appear in 5 minutes. So in the simplified scenario, we have two schools. We have school A and school B, and we have two types of students. Outcomes can be anywhere between 0, which is bad, and 1, which is amazing. The students that are of the first side, the students that are C, which is cheap, means that they have low costs. They don't require extracurricular preparation, so the utility is actually the outcome. The students that are expensive require some costs, and their utility of the school for the students is the outcome minus something that is proportional to the outcome. We can also make those utilities negative by subtracting some cost from it. And this more or less matches the idea of having underperforming students that transit in the middle of high school from one high school to the other, like in the no channel behind that, the US. We also model the student preferences, which originally are random, and then there are some recommendations which are made based on the past outcome of the students of the same time. There are two parameters that are important here. The first one is the accuracy of the prediction. We can think about it, a machine learning model that is perfect, it estimates exactly what happens, it has a great level of accuracy. But there is also another parameter, which is the trust. How much does the student trust the recommendations and adopt the recommendations of the machine learning model? The matching mechanism is just a simple random serial dictatorship, which means that each student students are ordered at random, and the first student in the order is allocated to the first school, the second student to their first school, their most preferred school that still has places, and so on. And the level of attack means how much does the student deviate from 1, we assume that 1 is always possible, and then how much they go to 0 for their optimal behavior. And there are many things that we can prove in this simplified setting. For instance, if there is perfect accuracy and trust, so the prediction knows exactly what has happened, has perfect observation of the history, and everybody trusts these implementary systems, and all students are of the same type and utilities are positive, then it means that the truthful interaction is actually Nash equilibrium. So we are happy we have good cohorts. Why is this the case? Because if there are at least as many students as places, then it means that nothing changes by strategizing. The school will receive a student in the end, and it will be of the same type because these are the only types of students that we have. If there is one student, because utilities are positive, they don't want to not to get the student because this will give utility 0 and they are actually worse. So this is a happy scenario. The other ones, even when utilities are negative, if all students are the same, again, there is no benefit from interacting strategically. However, when utilities are negative, and there is a chance for, let's assume that we have one student, the utility is negative, so the student will not benefit from taking the student, then of course they want to attack. Because after attacking, then they will not be allocating the student. After they deviate, the utility is 0, so they are just left with one negative utility, nothing they are done. On the other hand, without attacking, then they have an equal chance with the others too because of symmetry to incidence. This is the parenthesis. Now I'm back out of the math and I'm back at the summarizing the results. The first thing, the main takeaway of everything that I've said so far is that not all systems are interaction proof. Especially when utilities are negative, then you have a lot of problems. If schools can have a chance of getting the students, that they will strategize, they will interact strategically, and it will hurt the outcomes of the students. After one school attacks, then the other school will respond to attack that will precede harder. This will be their best response. And what we have here is a result actually from the simulation. We have the utility of school A on the x-axis and utility of school on the y-axis. This is the start-to point where everybody attacks at the level 0. Everybody interacts truthfully. And then the best response is to increase to a 25 level of attack by school A. If school A does this, then school B will respond to a higher level of attack that will have 50% in increasing their utility and lowering the utility of school A. And so on, we continue with best responses until everybody attacks at the level of 100%. This corresponds with all students having bad outcomes. It is a Nash equilibrium, but it's a Pareto dominated by the original state. So the original state is basically better for everybody. It's better for the schools, it's better for the students, but it's just no one given. Perhaps the most concerning part is that if we increase the trust and accuracy of prediction, this also increases the utility to other adversarial interaction facts. So if we make our decision support better and it is more accurate and students trust it more, then this means that people will have a higher incentive to attack the system because the system will be more responsive to the adversarial attack. I'm a school, I don't want students, I behave in such a way to signal that I'm not good at training students, reforming students efficiently. The system will pick it up because of the high accuracy, and the students will trust the recommendation because of the high trust. So it's not always that we make the systems better, but by improving trust and accuracy. And because going to the thing that is most related to our workshop today, those attacks increase inequality in the student appreciation. Here on the x-axis, you have the level of attacks by the schools, and we see that as schools start to attack more and more, then the average student welfare is decreasing for all students. But it's not decreasing equally for everybody. The students who don't have a lot of costs, then they will just maintain the same welfare as before. As students that require more resources and support, those will be exactly the students who will be targeted by the attacks, and we have lower welfare in the system. When looking at simulated results and trying more matching markets, key nearest neighbors, and more complex predictors, then what we see is that the actual results do depend on the characteristics of the market. So some matching markets are more vulnerable than others. And there are some solutions, like allowing the schools to really express their preferences. Because in practice, their preferences are not really expressed in many such systems. If we think about postdoc, for example, those preferences of schools are largely given by the locations of the students, for instance, or whether or not there are siblings, but not about what the schools really believe that is best suited for them. There are many questions that are open, and we are actively thinking about them. The first thought is that how do we test the extent to which people really attack those recommendations? Because it's really hard to find those answers. We cannot go and ask because nobody will say, yes, I'm attacking the system and I'm not behaving in the best way for the students or refugees. One idea that we had was to do experiments. So to really take some agents, reinforcement learning agents, or do experiments and to have human agents and see whether or not they will find those adversarial interaction, as in whether or not they will use them. And it's really important to consider the specifics of different application domains. Because so far I stick with the school choice example. But if we think about refugee assignment, utilities are always negative. So we are in a bigger problem than in the case of school choice. And moreover, the loop is more tight because the decision support system is not given as recommendations for the refugee. The machine learning prediction are fitted into a control filtration problem, and that they are used directly to see which refugees are matched to which locations. And the last part, that's perhaps the most important question, is can we intervene? And so far we found some interventions that could be efficient, but they are unfortunately mostly theoretical. So one thing is to let the institutions spread their preferences, which I mentioned before. The other thing is just to maintain some noise in the predictions. If the predictions are noisy, then there is less of an incentive for schools to manipulate. So this could be one option. And finally, we can make utilities positive, because when utilities are positive, the locations actually want to have people match to them, and this is better. So we can offset them by having some sort of funds that are associated with underperforming students who are refugees. But what is this number is very far-fetched brands. In any case, those questions aside, I think that the main takeaway of this talk is that as we add or improve the outcome-based predictions within those types of two-sided matching markets, we should also reanalyze the adversarial interactions and those incentives, because they can lower the welfare and they can lead to larger inequalities that are independent of individual pledge.
Any question from you?
I do have a question. So you say, okay, one idea is to keep the noise, but then you use alpha and beta. How are these two things matching your framework?
Yeah, that's a great point. So keeping the noise will be, alpha is the level of accuracy. So if alpha is high, then we have base numbers. So if we keep alpha high, it will be, schools will likely want to strategize. But if we go under they will want to strategize, and then as we lower it, they will still want to strategize until at some point they go low enough, they will handle it simple tweaks. So, and the thing is to find that threshold, because this is the optimum trade-off between still using the data in some way useful, but not to that point that we switch the figure of the school into structures. So this will be on the alpha side. The theta is how much trust people have in those systems. And those are actually, we don't model them as being correlated, but in practice they are sort of correlated, because if we lower the accuracy, then the trust will also fall. So I don't have a practical answer to this, but at the theoretical level, we can basically find that threshold. And yeah.
Yes.
So have you studied how government policy affects this? Like for instance, the school example, some countries there are quota on like how many disadvantaged children should be attending certain schools.
Yeah.
How is such thing that affects the results that you will obviously
That's a great point. And this also happens in the refugee science. So after they introduced it, they also have some quotas. And I was discussing this from somebody from the integration policy lab at theory, because they were saying exactly this, that if we have quotas and in theory everything should be fixed. It's not exactly like this, because even within quotas they are putting different types of agents. So the ones that will have the lower utilities or the higher costs will actually be still targeted in these scenarios. And there are also problems that arise at the intersections of protected attributes, which are very hard to tackle with specific policies on specific demographics, because the power of that was. So it is a solution, but I don't think it's a full solution to this.
So if you quantize like how much it affects, like how much it drifted back up, or how it does better, can you quantize it in the effect?
In the model, in the framework with the theoretical model, we can quantify it. I think on the list, just copy and I say, yeah, but I do measure do this. But it can be quantified. In practice, I think it's very hard to quantify, because we would need to specify the exact utilities, and it's very hard to put numbers of how much schools want prestige or locations benefit in the long run from refugee versus how much cost exactly it is per refugee or per student they pay them. So we will need two precise numbers. Thank you. Today I'm going to talk about our work on fairness in social impact civilization via optimum path. And this unit created from the series in collaboration with Shubham, which was a student dedication, Nicholas, with here, and Troy. Okay, so what is social impact maximization? Suppose you want to sell a product over a net, or make an information spread as much as possible. So social impact maximization is the problem of how to select the seed nodes, namely the nodes from which the information starts affecting, or the nodes to which they're gonna get the font factory in order to potentially promote your policy. You want to strategically select those nodes so that the outreach the information is massive. So this in principle is and can be part of it. So usually people propose some greedy strat. So you might select nodes in the greasy quarter of our degree, or you might adopt some greedy strategy where you myophically select the next best nodes either. Okay. Suppose now, yes, instead of setting a product spreading random information, you want to spread the news about the novel position in a math department. So here, the sensitive attributes of the nodes become important, right? Like you want to be able to reach in an equitable way women and men, so that you can ensure some equitability. So here it calls the problem of variant issue, where people try to solve the social issues by trying to ensure balance of these nodes that they will have. So this is important to select the nodes for the subcategories that they will totally set the categories that some provide a more a peripheral zone of the network would end up being magnetic. So we need to figure out something different, and so the social maximization problem on their side various good. So we'll assume the spreading mechanism to be as simple as an independent cascade model. It's not very important what I'm going to say afterwards, but just keep in mind that with probability key, the information is going to pass to the neighbors. We probably he analyze big does not. Okay, so what has been done so far? There have been many fairness metrics available in literature, but the key point of this slide is that all of them involved unexpected bad, which is dangerous, and I'm gonna tell you why. So consider this critical example. Consider the case in which in 50% of the cases, no one from group one is in the information, while everyone from group 2 does. And in the other 50%, the opposite happens. So although in expectation, this case would be classified as perfectly fair, what happens is that at each iteration, you can see that for each run of the algorithm, the outcome is either fair. Every time I run this social maximization algorithm, I would get that everyone from one group receives the information and no one for the other does. And although this example may sound artificial to you, it also happens to real. So we found some empirical evidence on a real dataset of the case in which, like, many people from one group receive the information and little people from the other group receive. So we want to be able to detect this equation. In particular, we want to be able to answer questions such as, when group 1 receives the information, will group 2 also receive it? And even if the two groups have the same margin of probabilities, will the final configuration always be fair? So here is our potentiating example. So consider this case. There are two outreach probability distributions. We call them gamma A and gamma. Gamma A is located onto the diagonal, while for gamma P what happens that in 50% of the cases, everyone from one group receives the information and no one from the other group does. However, those two outreach probability share the same marginals, meaning they share the same expected weight. However, if you look at the correlation aspects in the pool, you must be able to detect that they code two very different situations. So the key point, the idea is to use the joint outreach probability distribution to be able to capture those correlation aspects. How do we do that? We do that with the optimal transfer. So we want to be able to quantify the distance of the empirical, the outreach probability distribution gamma, from a desired distribution which is located on the diagonal. And we do that with an optimal transfer problem, namely is the problem of how to work one distribution, the empirical one, onto the ideal one, when moving a unit of mass from one to the other has a cost of 30. So in order to solve this optimal transfer problem, we need two main ingredients. First, we need to design a transportation cost. And second, we need a reference distribution. So regarding the transportation cost, we consider those two key aspects. So we assume that moving mass along the diagonal has a cost of 0 because it does not affect variable. What we are going to pay to move one distribution towards the other is instead the Euclidean distance from the starting point towards the diagonal. And here it comes a new fairness method we propose. We say that given an effort, we say to participant, the method is be generalized for communities. A socially proximity gesture algorithm is said to be brutally fair if the algorithm propagates in order to maximize its fairness. Here, where the desired distribution is the delta distribution located on the top right corner of the partition. Uh, Three key observations. The first one is that so this fairness is rated is between 0 and 1. It takes its minimum value equal to 0 in correspondence of the most ampere outcome, which represents the data represented by the data distribution in which a normal from modulo pressing the population and the most per that does, and obtains the maximum value equal to 1 and in correspondence of the reference distribution, which is the desired outcome in which everyone from a group receives the population. Given that the desired distribution is as simple as a delta distribution, this optimal transport problem that in principle could be very difficult to solve, it boils down to linear equation where you just create an average. So how do we put this in practice? We run simulation across different datasets, different probability distribution, different cardinalities of the six set. And we could observe four correlated patterns. The first one is a deterministic outcome located onto the diagonal. In this case, our metric and any metric based on an expected value will give you the same proportion. They would tell you the outcome is fair, so we don't gain much from what we are told. And this is typical of data sets in which there is a high cross group interaction, so we homomorphic as analysis state. The second outcome is probability distribution located onto the diagram, but with variance spreads over the diagram. And this is what happens if we lower the probability in a solution. The third case is the one from our motivated example. In this case, many people from one group can see people for patient and need the people from the other two. And here, if you think about expected value, you would end up on the diagonal, but our metric could be able to touch. It's not fair. Okay, the reason from this part, namely that for both the case in which no one from both group receives the information and anyone from both group does, they get the same fairness score. They are most on the diagonal, but arguably there is one outcome which is more desirable than the other, correct? So we decide to revisit our transportation costs and put up a trade-off parameters between fairness and efficiency. So here is how the map of the new cost looks like. So for beta equal 0, we only care about efficiency, but beta equal 1, we only care about fairness. So we now use this new method we propose to run a 6 selection per hardware. So given a tip of the social graph, an initial guess which can come from any of the degree practice or even the iterator. On top of that, we run our. So for a number of iterations, we start by searching around the initial yes, and with a probability which is depends on the difference of the data fairness score between the new guess and the old candidate. We replace the old guess with the new proposed one, and with a mid-top probability x0, we perturb our choice, and we select a totally wrong and we repeat is over and over, and in the end we get the season as for the highest bet, so it happens.
So here is how the algorithm performs. So the general, the red one is the effect of our algorithm compared to the base. And base T refers to the key strategy where you will start selecting the increasing order of update. And base G refers to the really strategy where nodes start selecting iteratively by taking the next optimal select. And the general effect of our algorithm is it to move the empirical distribution towards the data. And here at the contour, we see some lunatic plots. Again, on different dataset, different probability of propagation, and different cardinalities of the six. And what you can see, the red dots are the first power algorithm with a greedy baseline or a degree baseline. The blue square are a baseline without the referred response scale. And I able prefer tools heuristic that give impact on fairness and that are really to run on top of a green strategy or a strategy. So the general effect is to perform better in terms of fairness overall, and by some time group having like minor loss in terms of efficiency. So to conclude, I propose you a new fairness metric for social impact maximization that captures new fairness-related aspects. We leverage this new metric to design a new seed selection strategy that pays off between fairness and efficiency, and we show superior fairness performance with minor decrease decreases. When the importancy, the take-home message is that this metric I'm proposing is not relating to any dynamical aspects underlying the propagation under you can apply to any data picker fairness problem you might want to get. Do this, I talk your attention and map to the universe.
Any question from you?
Yes.
If we are referring the efficiency versus fairness, you mentioned you see it increasing efficiency, but in some cases you also see increase in efficiency. Please text right on the left for the hollow things by the A. The last ones that go there you see this over.
I mean, in terms of efficiencies, the baseline does better, right?
And if you look at the empty spare there,
Yeah, in this case,
so is that's something you expect, or because that showed that no, you paid off that the whole edges really so optimally.
not good. That's true. Like, maybe that's because of the stochasticity of the seed selection algorithm we deal with, and that's why randomly we can perform better sometimes. Because if you go here, there is a little probability epsilon to totally perturb the choice of the algorithm and go out from the baseline. But it's not something that can happen systematically. I would say our strategy always performs better for the what you said to the degree baseline.
So that how sensitive are users to that kind of
Well, there are many parameters going on. There is the dimension of the seed set. There is the beta fairness trade-off. I will be able to give you a say for what, so you will put some. We didn't run any sensitivity, you know. So.
As an issue of mutual authority, there's a capital L. So how that affect the calculation?
I will refers to the number of samples that you collect. Again, we didn't run any sensitivity analysis with respect to the number of simulation, so I will know. But yeah, we just run it a number of times. That depends on the diameter of the graph. So that's how we choose that. But I don't have a schematic answer for it. But yeah, that would be an interesting thing with for. Hey.
Any other question? Joel, they have a bit of fun.
I do have, sir. See, you say in the end that you can apply this to any data, irrespectively of dynamical aspects. But what if what you're doing changes and you are trying to change the distribution, but if you don't match your goal, so you don't end up in the ideal distribution but you are changing it, does it change the whole setup of your problem and you have to do with it there?
I mean, in the end, like, depending on your setup, if you mind the time matter actors distribution doesn't have to be on the other. Although that might affect the complexity generally period bits. But given that, I mean, is the point here is that the dynamics doesn't really matter, right? You just take the outcome, you take a snapshot, and even what you got. It could also come from a survey, like some dates. Yeah, exactly. Yeah, it is. What happened before is it doesn't really matter. The way in which you put that slash.
So my first question is, okay, and now it's directed a bit to you, but it also involves you too. So looking fairness from an industrial perspective is quite a different thing because you have to think about revenues, while fairness maybe goes against revenue. What's your perspective about this, and do you think that it's worth it to research into fairness at all from an economic perspective?
Sure, it is. It's not only revenue, but legal perspective as well, because we in the US in particular we have this very expensive cases in board fire. So to understand the impact of the revenue and risks and trust and so it's we are working actively, although I'm working, as I explained in this presentation, there's been the non-SEC way. We're trying by way of separation of concerns and then try to come up with that in the center structure so that there's the doubt, but it's I mean it's a pretty decent thing.
It wasn't fairness, but he said they're ramping up and what we're been trying to figure out who like that, right? Especially you look at that.
And it's about this separation of concerns is that even a possible thing. Can you separate concerns truly, you perhaps?
I mean, it's not trivial, but we try to distance models so that what I explained, I think you're in talk, but also to some people afterwards, is that we are called the path of this of model here, but we are even seek to not first success long term, and by
It compromise that short-term revenue then only left is probably justified the outcome revenue perspective. We are just quite a bit better than our competitors, and they may expect that but more heavily by a smaller market. And it is also common, separately something that
you haven't done one researcher there is there's a ideas that only US are smart and right on in
that perspective, where do we see, for example, you are full engineer, you are a computer scientist, where can we try to bridge what's missing maybe in the what's the perspective?
One thing I was thinking about is that what I want in computer science work is that to set up some optimization value, make all the objectives, but it's really hard to know what the ultimate solution is. So the problem is in your part, like you have with another router within like the population hierarchy and a sprawler. So I think it's nice which the decides to like come in to show that give you some approximation algorithms and we can get closer to optimal solutions. Sometimes when you to fairness analytics, these types of problems, the bigger injuries where you say like underlying information and they being fair and being more efficient on pods, because if I reach more equal, then I'm actually more efficient. And if I can discover new communities, I'm both worker and efficient. So I think there are particular problems to be discovered very when do a market discovery and industry and so on that can bring subjectives a bit more aligned. So I feel a bit more hopeful, and I think of the role of computer science is to like tell us how much we can gain to like formulation of different objectives in a more aligned way, rather than just on the trails, which sometimes happens, sometimes.
That is a different thing.
Yeah, so Europe is different from US to have this AI Act. So that's a legal requirement. So speak controversy how AI can actually be implemented. So many things are uncertain. Then the biggest principle for AI Act to safeguard basic human rights. We identify what's meant by human rights. But then this third is the smallest principle that is behind this AI Act. So I work with several companies and they are asking Linear try to make sure their practice is AI Act treated, and they will not be penalized in the end because some of their algorithms turns out to be not AI Act compatible. So in that sense, I think it's not just a wish to prove success of algorithms is very large, but it's also very sensitive. So there is a legal pressure nowadays for this to be extended.
If you want to jump in, please do, because I tend to have a lot of questions that's not like this. So I have another question. So generally, so if you look at the snapshot of data, I agree with you that, okay, you try to be fair in that regard. But since you, for example, make an advertisement campaign, sell a product, and so on and so forth, or rank something, what happens is that you are changing actively a distribution. So you introduce the feedback that basically Stefania showed. And how are you now coping, for example, in the computer science community, with this kind of shift that you are expected to see, and how fairness and the features that?
And that's a great question. As computer science is a big might be it in about is in the long run. In, for example, on the settlement prediction, it is saying about it, oh, the distribution about that's changed based on side there is a prediction. So which will change the features that people have basically, and then it got expedition and so on. So think about it in equilibrium, then you can see what you want to define should fit to how people likely have. You don't always know that, so you need to cross some well circuit to estimate, which I'm sure it can surpass much more in terms of experimentation, but we can at least gather those insights, model it, do some thorough analysis to understand it. I think you need to incorporate this long narrative bits into your design algorithms.
I agree, and many backups say that as sponsored inside, it's non cross threat. One thing is to use diction of the lack of any use through recognition and we might gaze up and see what add and the question what works the monster meantime. Run something started.
It's subgerable, but I keep the best programs.
Here we have guarantees for some information. This is a supervised learning of the periodic cases the evaluations in a per reach and put over any is about overseas as per as during a baby test well to deal with that.
It's like a privacy a virtual policy. That is built up by control engineer because there is a biological aspect you can apply. So there are many privacy concepts, differential currencies or that is easy to become to settlement and ecosystems. So similarly, I also hope Nancy can avoid the worship of powers. And there are concepts, but sees the idea of distribution business has a lot of potential to be a dynamic first. So if we do agree, dynamic aspect in a sense is more important in this application. We should always learn that idea, that is definition.
Indeed. I agree. And another aspect, so you mentioned bottles. So in this context where you have social influences, you have so many, wouldn't say random aspects, but the human is evolved and if and assume the human is rational, might not be the case. So how do you cope with this kind of uncertainty you have?
On that, I think recoveries can be expressed particular defect related on population. Dashing a board of the fears as responses and fear analysis and so on. So I think it's a real core like how the big breaks to come in and now it's what's the impact both that you design all of that in a way on a population that can has challenges as we incorporate in the ecosystem with those interactions between interference. On your second sentence, which means that their data distribution changes. But with these tools, there are ways to like put it into a stable brain and to tell as well effective this platform this is computation. And with that, we don't really test out the behavior because we call it its impact. And then on we can tell why both is she did it. She's made the sound like just the else in order to drop or to have to be about it. So I see that as curious. I kick them off as a sample. Something at a very high level, and more experimentation in positive platform with positive for instance as a role to like colors actual impact, but they're different now. And then I wonder how industry does that too, or how you find experimentation useful in understanding design, especially in classes that are similar to model and search, also like products and practice and so on.
Experimentations on even mass number of researchers on daily was rare. That's where bread and butter. The castle assaulted with Rosa that probably there's a lot of actions online that would happen very long show mad. So it's cause intelligent. So enterprises care no more about the incremental conversion. One thing is that we can predict if the user convert, but maybe it will convert the other one that's the regression, and that requires more comprehensive experiments. You need us much more, much better problem to solve.
Just way to reach out to publics, not research, push the lab. So. An example of this advertisement campaign about renewable energies, we know that we want more households to install solar panels. But then we can make all kinds of assumptions about how human behave, how they respond to legal tax. But if we do have a lot of data on the already available in ECC in the dowries, know the household distribution, their economic situation, and then also because this created a similar campaign in the past, but we do it to get the trust from little business owners. They can give a certified version and data effect to us for us to have a very targeted to the campaign and research project. So I guess there are efforts to be made as a researcher. We can make all give more sophisticated, but there's also another approach trying to involve social hubs and try to gain access to their data. Yeah, to you, yes.
We obviously have lots amount of data, and we do have university collaborations, so we're trying to navigate about how to the proper way. So,
in principle, we have super Turkey relationship.
purpose, Maybe. You started talking, you talk more.
Yes. I suppose so. Their context in which fairness is not actually measurable. Like, for example, recommender system stuff like this, like feedback load, like causes opinion polarization and stuff like this. But you cannot really get statistics of what those recommender system are putting. Where do you think the incentive to mitigate this undesired effect came from in this unfairness, kind of a fairness, maybe differently related from automatic decision-making systems came to account?
But I'm not happy accepting that the hiding fairness is. I would think of like this content outage for invest content outage preferences. It's hard with one measure as Becky in a lot of years like asked some about tree or the some resource that they has to the bottom of that meeting. Think that there's something more natural. Though. There's like engaging out about cap is that related to Sonia, related first for non negative enough, but it's about housing, employees and things like that. Against care about the access to first this that gets is contributory can be something a little bit more measurable. So I guess we need to do my interest in like what is the resource you're trying to allocate? Is it something that care about in first of access and that
Yeah, what I was thinking was more like views sharing, what recommender system try to do is try to maximize engagement, meaning like you rely on confirmation bias and trying to match people's interest by like exaggerating their own opinion. But how like it's not about an advertisement to stuff where you can get statistics out of it, but it's just about the revenue of this company that wants to get money from your time spent to the platform and the advertising. It's you see, but that's not the advertisement is not the center of the optimization problem.
That's an important point. Out of that answer, that's I think with regard to the site structure, so that's basically arranger up there.
As a software share, I openings not gonna hit offended. So there's one young university called the Digital Inclusion, organized by the Digital Media Group, the Diversity of Social Science and Combined. So I, in the title part is like still there, in there, but then everything's so subject. The fairness is fulfilling. So I feel I have been treated unfairly because my child cannot be put to this school gone. So there's nothing quantifying. But the study will be the still very athletic eating with their fields. So I think we realize that if by starting involved of trying to quantify everything and try to compare everything, that's already a warning level starting point. If you calculate really to be varies but be say concept that's important for those people sitting in the conference, therapy, I can calculate according to my calculation. This I will be spared, but to them that's something important. So I didn't see this big spectrum, broadly subjective way of sport developing way of picking up viruses to the cases where we try to come back. I keep a capability to improve. I think there are lots of even layers, even a little. We have to be careful about trying to be that is a very precise, very less and that's all before. But what we want to really impact the people. How this tech skills and those algorithms, we have to find also go to their directions.
Hey, I know what this brainstorm there's the points that I think all the yes, I agree that it reminds me of the ontisha social sciences so about and delivering that the ever free greenest community can solve the careers and now which they are having something. I'm not happy that somebody else got something I did not because they had the very formal solution of this regard in a like human ML like interaction with this missioner not community to get this like a measurable events how we go guessing various in different lights serving our patients a survey designs. Another one it's very like the Tyrians, like how we correct this statistic. We also learn especially like it was handless and like says about our design all the programs that we have. And then we have this more mathematical variables, for example, like, oh, I just want some like guarantee, like some statistical parity with an rapid parity has nothing then we could kill. But I think bringing them to like I think these sort of monkeys exist in all this field. Bringing them together is not eager to need their own how to do it, and we might not end up with being satisfied all once. It's good. The main factor.
So the life life by Tom and Mastery is health and benevolence. So the outcome is 5 people will equal certain covered aspect of the art is also life. And so then the requirement is to have the hustler, you have to have people from social science as the GI. So I'm making the hustler for technical history. Because all my co-PIs way up on social science diamond. So I do this for fundraisers if we're trying to force people to you can only get the value from studying the lab, but if you first have such monsters that's quite a shabby operation. But you also help me the face of the writing of proposal and it is like the picture good because adding all the detail below the integrated it was is ECC but E spells just everything for that at least.
Well, from complete outsider, like you not discuss fairness. Another topic in machine learning is also explainability. Now, how can you make use of explainability of the underlying onward decision making when you want to develop fairness or assess fairness on both positions? Very different. That's great. Are these things that are actively like exploited or is it always case by case?
So I can share survey on this. It's a triangle will have privacy, fairness, and interpretability. So that each of them there's tension, is cooperative, right, and synergy in the political posture. There is a survey paper for all the pairwise distribution models. I can probably be but the conclusion is for every edge of the triangle, use both of it. They can be consistent, but they can also be compact.
As is to topics or directions of this functionality and see a particular gives you able to bound this get them also some are easier to understand and look at our decision some are non-mass, but again they are the same. So there's a big question of like how do you choose to take that at the end? Yeah. You may want to choose the ones that are like still as efficient, how they're right. The other line word that I was finding using is asking why did your ability where I know that you better model weights directly, but they might in fact you might have most immediate recourse. And recourse is where care and that's a lot of work I have and their fairness and like models that are trying to achieve fairness also are recourse friendly. So if you get a loan, you get you back get subject this particular to an output during the 10 we have some information about what you of course some of the information sources is like just making your money to lose more, but maybe this other type of information quite presenters so that centralized manual Newton with the system about a truthful effort so you can change something. And I think that's it's heavily studied. I love that line of part, but
Remote ceremony on like human supervision of the machine vertical algorithm takes this is on special uses to application less juridic cases and this. We think there should be a human involved in it, or how can we make the post decision totally black box and that
You human to overcome efficiencies and optimizations and being used for the rest.
that like I mean those system comes into play because that they are very efficient. They're able to like
handle a huge amount of data without having someone loading up all the paperwork and all the stuff. But there are some they apply it across different applications, right? Some are more sensitive than others. Say you put a person in jail because of it is historic that maybe that there is more than that.
I mean, in my line of work, and nobody ever died or was a jail.
Yeah, exactly.
But we was still, I mean, our building kind of with the child from AFR. You'll always be touch cases. I mean, we're at any given time, right around maybe 500,000 active simultaneously. And if that is a body to die, anyway, assisted to make right decisions and would say that talked about you all the speed to the speed so it really starts to monitor the voters to then first of all was inside stand up the front level chairs and trenches laid eyes master alerts so that we had to use our recommend others who deep dives in 6 other but that's I mean the north stars we don't mean that just we but below this and practice it says it's a shooting point but get the point but you don't need to shoot that if it gets there you fire so
Yeah, it's not that was it. I can go to reverse for the shoes that she belong by. And in the moments that we buy for the visualization, how we're not perfect, getting on some part of the data. How do they learn to become better at the part that they require some key supervision? So there's a recent article showing that if you keep training models on just synthetic data generated from their own, they get in the black box and you don't allow such a combination and all splash over time because they can't get their help from their own errors. And what they show is that they do require something in the data labeling, just the big customer image computer that needed LLMs shows be like much very don't use it. So you really need it in some way in order to correct the models and change even just accuracy can really to make them better over time. And for the wall when it be given in order to make the system wall is actually they enter theirs. Okay. It's not good nor fair.
That's a little example because this language now so for application in I would not again simply little in alpha. So some parts. I could imagine another applications if there's a big consequence or series of couple points. I will solve code below symbols and house will help you.
You do. I mean, I don't see it. I could also imagine that this could be appropriate because when you pass a dashboard, which you should supervise on the member, but maybe probably next period that you understand, may chooses then something about the network very much use, but in the end, one one's maybe not quite good, so this is also it could measure as possible each of others, especially for associations.
Yeah, there is a law that distinguish the share of experience if something is up. So in the medical, the liability marks causing indicates the visual stuff the hospital each hardware they work there's and patients. And then they're trying to that also allow the runner to create a liability law vessel to dig into automatic locked process. Just they have to have a identity law. If a human they was fishing, they try to hit at our serious. Because we find this oriented the conservation, but this can be a very long process. So this really do.
Adding yet that romantic ones are the sense the other terrible excerpt is that it can have multiple experts in the water load as that. There are multiple experts in product and it's that already you can put their decisions together and learn this the step or that at the extra level that I call it that one. Just like on the biggest grades first like that as the energies supply for create society. Here I receive it unless all registers are add, which is an area like gates.
But it can backfire also. So let me explain what I said earlier. I said that we represent among advertisers, but in reality, it's even more bright and
The guidance has actually was also said we mentioned 500,000 from paid every game.
time. So we almost all those there's an agents between us and that. So the agents, that kind of disciplines that have the advertiser manage campaigns. They don't provide optimization to one. We provide optimization for. So the answer is little none for the advertiser or us. So they justify their existence by intervening and doing things. So if our models were perfect, I mean, they would still want to go in and mess around the system. So that happens a lot, but they are overdoing that. So that we have to tell them that and the answer is being to not headers control system. They have some analysts at one of the agents accept change set point value to both system making 1,000 tags a day, and on that creates is a built system. So they are needed and they go wrong, but they're off abusing systems.
What he thinks that as might it happen that if you have this kind of cases in which people are abusing, let's say, their power over the model, and then you say, okay, but I'm experimentally collecting data, then can that be dangerous? Maybe not in the long run because you fix the issues, but if you look at Snatch,
Our experiments are the experiments that they have to experiment.
both at the end.
No, for sure. I mean, we're having this challenge, and that there's a lot of pressure about what there was. A system may want to add all these levels, but they can put up it basically demands that automated testing and that's that introduce more feedback loops and that will eventually stabilize the system and also compromise our ability. So our experiments at there. But that is really the name of the day. It does not decide
As firm as if we are Nostradamus, that's
Let's say that is because I don't see that much explored actually in the research community. So researchers get the data, but they don't. Okay, it's very difficult to design these kind of experiments where you close the loop on a social or socially relevant problem, let's say. But then how do you design an experiment where you're robust to this kind of data?
Well, I don't know if there is sort of any amount of perfect solution, but we definitely have to just have that. Be mindful that some agencies or advertising they wanted to then interfere with companies that they belong to them, and now we have to run experiments that will only involve that company, but involve companies managed for many other advertisers. So that the sales interference is not taking place across the board.
And across communities, the struggle also. So this everything is experimentation on the issue. We are not allowed by the being and understanding what this get for new models. Besides GPD years, I think there is that much corporate is a bit a nice direction there. So that's a legal work and strategy is CKC goal based recommendation needs also in your gear. Saying we can't get full guarantees. You need to make some assumption like this so that you need to someone like give this deal and this thing you invest that I think it's a very rigid idea but the one start that I've seen was mostly design like what elements in that course need to strat into the model in your gear as a gap like design experiments that are like completely destroyed like restaurants and that and
But when I definitely encourage all of you to, if your papers work with real data, real aggregated data that has made subjects of all of these reviews, because producing simulate data, or if you work with a company, you ask a company to provide clean data. I mean that's 95% of the work just actually overcome the try to be associated with and with the undue data. So
When you spoke about, for example, this kind of collaborations with people that are in law, in social sciences, how easy do you think, or you have experiences for you to translate what you need in order to run models, learn something to them, which might not understand your needs?
Yeah. So first they have to set up a couple goal that we have the call for proposal that we are index on. Those and how to have some baseline trust on each other.
And then I think we have to have people to display our role in part very huge possibility function with human help, but they need to talk about improve things.
And they try to avoid the reach full kind of language. I think everyone understands.
And then I think it's also be to start with the data. I will have key I'm sharing about data applicants. And from the data, email to discrete storage, converge to work on via the bridge, on the bridge.
So then we can try to handle what this causes.
I can work and last thing you said to start the quality and suddenly Tony. So and that's something but for her because it's something behind that can be understood by people to be back. So we had this literally full control town where there's a bit the first science engineer and product management says so when basically any time or in the company people that wouldn't be able to put the open functions, but also the energy to use this is sanitary. But everybody can understand a graph. I mean, if you look at some plot, then if it behaves like this or it behaves like this and that, but that's just something.
And I found that very useful, very well. I got on the same page. So,
And eventually explain them your aids so that they can do something, even you interact with them.
Exactly. So that's that enrich that about talking about the problems. But have the people in this society explain why they're unhappy. But how they're managing and update, then we can translate that into math and models. We did solve the problem, but we want to present the equations that are lack, but we implement the system and demonstrate qualitatively
why the UVA works. Imagine that at the last one, large scale experiments and the ones we use a signal.
I have one last question, but maybe it's more there to you. Since you are the only control engineer among the time, and we are as a control conference, you are a control engineer too, so you send this lie to me too. Sorry, indeed. We're from an industry, but you are still a control engineer. So, what do you think could be the role of our community in this kind of huge field that is eventually great with PMS?
Yeah, I see for the control health several impacts.
Solenoid thousands robots are also of their reactors
or kind of tendency with RPs. So, copy that virus.
and the money is the angle for us to show us a statistical formulation and in the idea feedback close to both control ideas can find new meaning
such socially organic contexts. It's also very easy for us. We kind to progress is all it is having a small way the street. With only under events minutes. Now we shall want the scientists see. Our happy has companies to make care open to SDO partnership to see that us currently here moving with the children cars about the areas.
Yeah, that's the from upstairs. I agree with you said.
Control the own actual economy was also the control the head of the going. Yeah, that was on think of the not of the silverware and the in this particular area. They're also taking terms of down the feedback something the city and the post on this the best was
Very good. You can in mind that some interesting mass regulation but after pushing run of suddenly control but it's something. It's very exciting.
I think ever since I went into on network, something a lot of people back on that, but a lot of people that so implement on both algorithm, but most of them don't realize they may not even call it feedback control, but they're also reinventing something that already exists in literature.
Replace the words and that's the word. Especially that's the word. Or say they at the end of the sub talk, there's some a word that it said.